Antimatter. It sounds like something out of a science fiction novel, but it's very real and incredibly powerful. Imagine a fuel so potent that just a few grams could propel a spacecraft to the outer reaches of our solar system. That's the promise of antimatter energy. First discovered in the early 20th century, antimatter is the mirror opposite of the matter that makes up our universe. When antimatter comes into contact with matter, they annihilate each other, releasing vast amounts of energy. This energy potential is what makes antimatter so exciting for space travel. Currently, antimatter is produced in particle accelerators, where high-energy collisions create tiny amounts of antimatter particles. However, producing and storing antimatter is extremely challenging and expensive. But the potential benefits for space travel are immense, making this a hot area of research. Antimatter propulsion concepts are varied and fascinating. One idea is direct annihilation propulsion, where antimatter and matter are combined to create a high-energy explosion that propels a spacecraft. Another concept is antimatter-catalyzed nuclear pulse propulsion, which uses small amounts of antimatter to trigger fusion reactions. The theoretical efficiency and speed of antimatter propulsion are unparalleled. Traditional chemical rockets are limited in how fast and far they can travel, but antimatter could revolutionize our approach to space exploration, potentially allowing us to reach distant planets and even other star systems. Despite the excitement, there are significant technological hurdles to overcome. Producing antimatter in sufficient quantities is a major challenge, as is developing safe and efficient storage methods. Containing antimatter safely requires advanced magnetic fields and sophisticated technology to prevent it from coming into contact with matter prematurely. Comparing antimatter propulsion to other propulsion systems highlights its potential. Chemical rockets, while reliable, are slow and inefficient for long-distance space travel. Nuclear thermal propulsion offers some improvements, but nothing compares to the promise of antimatter's energy density and efficiency. The potential benefits of antimatter propulsion are staggering. Imagine reducing travel time to Mars from months to weeks, or sending probes to the outer solar system in a fraction of the time it currently takes. With antimatter, deep space exploration and even colonization of distant planets could become feasible. However, the risks and ethical considerations cannot be ignored. Antimatter containment failures could have catastrophic consequences, and there's the potential for weaponization. Ensuring the safe and ethical use of antimatter technology will require international cooperation and stringent regulations. Current research and development in antimatter propulsion are promising. Leading institutions and private companies are investing in this futuristic technology, pushing the boundaries of what's possible. Recent breakthroughs in production and containment bring us closer to making antimatter propulsion a reality for space travel. Creating antimatter starts with particle accelerators. These machines smash particles together at incredibly high speeds. When they collide, antimatter particles are produced as a byproduct. The process is far from simple. High-energy collisions require immense amounts of power. The result is a minuscule amount of antimatter, often just a few atoms. Particle accelerators like the Large Hadron Collider are at the forefront. These facilities are among the few capable of generating antimatter. They are pivotal in our quest to harness this exotic form of energy. Another method involves radioactive decay. Certain types of radioactive materials naturally produce positrons, a form of antimatter. This process, however, yields even smaller quantities. Despite these efforts, production remains limited. The quantities produced are far too small for practical applications. Scaling up production is one of the biggest challenges facing researchers. Storage of antimatter is equally daunting. It cannot come into contact with regular matter. Special traps using magnetic and electric fields are employed to contain it. These storage devices are known as penning traps. They create a stable environment where antimatter can float in a vacuum. This prevents it from annihilating on contact with the container walls. Maintaining these traps requires sophisticated technology. The magnetic fields must be incredibly strong and precisely controlled. Any instability could result in catastrophic loss of antimatter. Producing antimatter also involves significant costs. The energy required for particle accelerators is enormous. This makes antimatter one of the most expensive substances to produce. Research continues to seek more efficient methods. Innovations in accelerator technology could reduce costs. Finding cheaper production techniques is critical for future use. One exciting avenue is laser-based production. High-powered lasers can potentially generate antimatter in more practical quantities. This method is still in experimental stages, but shows promise. Another approach is antimatter harvesting. Cosmic rays naturally produce antimatter in the upper atmosphere. Capturing this antimatter could provide an alternative production source. This concept involves using spacecraft with magnetic traps. They could collect antimatter from cosmic rays during space missions. Though theoretical, it's an intriguing possibility. International collaborations are crucial. The complexity and cost of antimatter research require global cooperation. Joint efforts may accelerate advancements and overcome current limitations. Advances in antimatter production are pivotal for future space travel. Continued research and innovation hold the key. As technology progresses, the dream of antimatter propulsion inches closer to reality. Particle accelerators are crucial for producing antimatter. These massive machines propel particles to near light speeds. The collisions they create are intense enough to generate antimatter. The most famous accelerator is the Large Hadron Collider. Located at CERN in Switzerland, it spans 27 kilometers. It's the world's largest and most powerful particle accelerator. Inside the collider, protons race around the circular track. They are guided by powerful magnets. When they collide, the energy released can produce antimatter particles. These collisions happen in a controlled environment. Detectors around the collider capture data. Scientists analyze this data to identify antimatter particles. Creating antimatter is just one of many uses for particle accelerators. They also help us understand fundamental physics. Studying these collisions reveals new particles and forces. Smaller accelerators exist worldwide. While not as powerful as the Large Hadron Collider, they still produce valuable antimatter. Universities and research institutions often operate these accelerators. The technology behind particle accelerators is complex. Superconducting magnets are essential. They generate the strong magnetic fields needed to guide particles. Accelerators also require precise timing. Particles must collide at just the right moment. This synchronization is achieved through advanced computer systems. Antimatter production in accelerators is highly efficient. However, it's not without challenges. The high-energy environment poses significant risks and requires rigorous safety protocols. Once antimatter is produced, it needs to be stored immediately. Magnetic traps within the accelerator capture the particles. These traps prevent antimatter from annihilating upon contact with matter. Research into improving accelerators is ongoing. Scientists aim to increase their efficiency and output. Advances could lead to more cost-effective antimatter production. Particle accelerators also have medical applications. They produce antimatter for PET scans. This imaging technology is vital for diagnosing certain diseases. The role of accelerators in antimatter research is irreplaceable. They are at the forefront of discovering and harnessing this exotic energy source. Without them, our progress would be significantly hindered. International collaborations often utilize these accelerators. Scientists from around the world come to facilities like CERN. This cooperation fosters innovation and accelerates discovery. Future accelerators may become even more advanced. Concepts like linear colliders and plasma Wakefield accelerators are being explored. These innovations could revolutionize our ability to produce antimatter. Storing antimatter presents a significant challenge. The main issue is that antimatter annihilates on contact with matter. This requires it to be kept in perfect isolation. Magnetic traps are the primary method for storage. These traps use magnetic fields to suspend antimatter in a vacuum. This prevents it from touching the walls of its container. One type of magnetic trap is the penning trap. It combines magnetic and electric fields. This creates a stable environment where antimatter can be held. Maintaining these traps is technically demanding. The magnetic fields need to be extremely strong and precise. Any fluctuations can lead to the loss of antimatter. Creating a perfect vacuum is also critical. Even the smallest particles of matter can cause annihilation. Vacuum systems must be maintained meticulously to ensure safety. Temperature control is another challenge. Antimatter traps need to operate at very low temperatures. This reduces the energy of the antimatter particles, making them easier to contain. Cryogenic systems are often used to cool these traps. They employ liquid helium or other cooling agents. These systems must run continuously to maintain the required temperatures. Storing antimatter also involves significant energy consumption. The magnetic and cryogenic systems require a constant power supply. This makes antimatter storage both complex and costly. Safety measures are paramount. Any containment failure can result in a violent release of energy. Facilities storing antimatter must adhere to stringent safety protocols. Even with advanced technology, long-term storage remains difficult. The systems must be maintained without interruption. This poses logistical challenges for extended space missions. Researchers are exploring new materials for containment. These materials could better withstand the conditions required for antimatter storage. Innovations in this area are crucial for future applications. Portable antimatter storage is another area of interest. Developing smaller, more efficient traps could enable practical use. This would be a major step forward for space travel. Antimatter storage also raises ethical considerations. The potential risks must be weighed against the benefits. International guidelines and regulations are necessary. Collaborative efforts are essential for overcoming these challenges. Sharing knowledge and resources can accelerate progress. This cooperation is vital for the future of antimatter technology. Advancements in storage technology will be pivotal. They will determine how effectively we can harness antimatter's potential. Continued research and innovation are crucial to making antimatter a viable energy source for space travel. Annihilation reactions occur when antimatter meets matter. This interaction results in both particles being destroyed. The process releases a tremendous amount of energy. The energy released comes from the complete conversion of mass into energy. According to Einstein's equation, E=mc², even a tiny amount of mass can produce a vast amount of energy. This makes annihilation reactions incredibly powerful. When a particle of antimatter collides with its corresponding matter particle, they annihilate each other. For example, a positron, which is the antimatter counterpart of an electron, will annihilate an electron. This reaction produces gamma rays. Gamma rays are high-energy photons. They carry the energy released from the annihilation. These photons can be detected and measured, providing evidence of the reaction. The efficiency of annihilation reactions is unmatched. Unlike chemical reactions that release energy from molecular bonds, annihilation converts all the mass directly into energy. This makes it an ideal energy source for propulsion. However, the intensity of this energy poses significant challenges. The gamma rays produced are highly penetrating and dangerous. Shielding and safety measures are essential to protect both equipment and personnel. Controlling annihilation reactions is another hurdle. Spontaneous annihilation must be prevented until the energy can be harnessed. This requires precise control over the storage and handling of antimatter. Harnessing the energy from annihilation requires advanced technology. Directing the gamma rays into a useful form of energy, such as thrust, involves complex engineering. This is a key area of research for antimatter propulsion. Annihilation reactions are not just theoretical. They have been observed and measured in laboratory settings. These experiments provide valuable data for developing practical applications. The potential applications extend beyond propulsion. Annihilation reactions could be used for energy generation. Their high efficiency makes them an attractive option for future power sources. However, practical implementation is still in the future. The challenges of production, storage, and control must be overcome. Ongoing research aims to address these issues. The power of annihilation reactions offers tantalizing possibilities. They could revolutionize space travel, allowing for much faster and more efficient journeys. This potential drives continued interest and investment in antimatter research. Understanding the mechanics of annihilation is crucial. Detailed studies help scientists design better containment and control systems. This knowledge is essential for safe and effective use of antimatter. Collaboration across scientific disciplines is necessary. Physicists, engineers, and materials scientists must work together. Their combined efforts are key to unlocking the potential of annihilation reactions. As technology advances, the dream of using annihilation for propulsion becomes more achievable. The energy released could propel spacecraft to unprecedented speeds. This would open new frontiers in space exploration. The energy yield from antimatter-matter collisions is extraordinary. When antimatter meets matter, their mass is converted entirely into energy. This process is far more efficient than any chemical or nuclear reaction. In practical terms, 1 gram of antimatter annihilating with 1 gram of matter releases about 90 terajoules of energy. This is equivalent to the energy produced by a 21 kiloton nuclear explosion. The potential for harnessing this energy is immense. The energy produced is primarily in the form of gamma rays. These high-energy photons carry the energy away from the site of annihilation. Harnessing this energy effectively is a significant engineering challenge. Converting gamma rays into usable energy requires advanced technology. Methods such as gamma-ray lasers and photon propulsion are being explored. These techniques aim to direct the energy for propulsion or power generation. The efficiency of antimatter-matter collisions makes them an attractive energy source. Traditional fuel sources are vastly outmatched by the energy density of antimatter. This could revolutionize the way we think about energy and propulsion. However, the energy release is extremely intense. Containing and controlling this release safely is a major concern. Shielding and energy conversion systems must be developed to manage this power. Current technology is not yet capable of fully harnessing this energy. Theoretical models provide a roadmap, but practical applications are still in development. Researchers are working on ways to make this a reality. The potential uses for this energy are vast. From powering spacecraft to providing energy for remote outposts, the possibilities are exciting. The high energy yield could make long-duration space missions feasible. For space travel, this energy could reduce travel time significantly. Faster journeys to distant planets or even other star systems could become possible. This would open up new frontiers for exploration. The high energy yield also has implications for energy storage. Antimatter could potentially store large amounts of energy in a small volume. This would be beneficial for both space missions and terrestrial applications. Economic considerations are important as well. The cost of producing and storing antimatter is currently very high. Advances in technology could reduce these costs, making antimatter a viable energy source. Safety is a critical factor. The immense energy release requires stringent safety protocols. Ensuring the safe handling and use of antimatter is paramount. International cooperation is essential in this field. Shared knowledge and resources can accelerate advancements. Collaborative efforts will be crucial for overcoming the challenges. The potential of antimatter-matter collisions continues to drive research. Scientists are optimistic about the future applications. Each breakthrough brings us closer to realizing the potential of this incredible energy source. As we move forward, the focus remains on making antimatter a practical and safe energy source. The energy yield from antimatter-matter collisions offers a glimpse into a powerful future. This journey is just beginning, with many exciting developments ahead. Antimatter propulsion is a cutting-edge concept in space travel. It involves using the immense energy released from matter-antimatter annihilation. This energy can potentially propel spacecraft to incredible speeds. The basic principle relies on storing antimatter and allowing it to interact with matter. This interaction results in a complete conversion of mass to energy. The energy produced can then be directed to generate thrust. One proposed method is direct annihilation propulsion. Here, antimatter is injected into a reaction chamber containing matter. The resulting explosion produces high-energy particles that are expelled to create thrust. Another approach is antimatter-catalyzed nuclear propulsion. In this system, a small amount of antimatter triggers a nuclear reaction. This enhances the energy output of conventional nuclear propulsion systems. Beam core antimatter rockets are also being explored. These rockets use magnetic fields to direct the products of antimatter annihilation. The expelled particles generate thrust, pushing the spacecraft forward. Theoretical efficiency of antimatter propulsion is unmatched. Unlike chemical rockets, which are limited by the energy in chemical bonds, antimatter propulsion converts mass entirely into energy. This leads to far greater thrust per unit of fuel. Antimatter propulsion could dramatically reduce travel times. Journeys to Mars or beyond could take weeks instead of months. This opens up new possibilities for human exploration of the solar system. Designing a spacecraft for antimatter propulsion involves several challenges. Storage and containment of antimatter are critical. Magnetic and electric fields must be precisely controlled to prevent premature annihilation. Safety is a major concern. The energy released from even a small amount of antimatter is immense. Robust shielding and containment systems are necessary to protect the spacecraft and its crew. Efficiency in energy conversion is key. Current technologies must be adapted to harness the energy from antimatter annihilation effectively. This involves advanced engineering and innovative solutions. Research into antimatter propulsion is ongoing. Scientists are developing new materials and methods to improve storage and containment. Innovations in this area are crucial for making antimatter propulsion viable. The potential benefits are driving significant investment. Both governmental and private entities are exploring antimatter propulsion. The race is on to develop the first practical antimatter-powered spacecraft. Public interest in antimatter propulsion is growing. The possibilities it presents capture the imagination. Media and educational programs are helping to raise awareness of its potential. Collaboration between nations and institutions is essential. Shared research efforts can accelerate progress. The global scientific community is working together to overcome the challenges. Antimatter propulsion represents a leap forward in space travel technology. Its potential to revolutionize space exploration is immense. As research continues, we move closer to unlocking the power of antimatter for space travel. Direct annihilation propulsion is one of the most exciting concepts in antimatter technology. It involves directly using the energy from matter-antimatter annihilation to propel a spacecraft. This method promises unparalleled efficiency and speed. In this system, antimatter, such as positrons, is injected into a chamber containing matter, like electrons. When they collide, they annihilate each other. This annihilation releases a burst of high-energy gamma rays. These gamma rays carry immense energy. By converting this energy into thrust, a spacecraft can achieve incredible velocities. The challenge lies in efficiently harnessing and directing this energy. One approach is to use magnetic nozzles. These nozzles direct the gamma rays and other particles produced in the annihilation. The expelled particles generate thrust, pushing the spacecraft forward. Another method involves converting gamma rays into charged particles. These particles can then be accelerated and directed to produce thrust. This requires advanced electromagnetic technology. Shielding is crucial in direct annihilation propulsion. The intense gamma rays pose a significant risk. Advanced materials and designs are needed to protect both the spacecraft and its occupants. Efficient energy conversion is a major hurdle. Current technologies are not yet capable of fully harnessing the energy from gamma rays. Research is focused on developing new methods to improve efficiency. Cooling systems are also essential. The annihilation process generates a lot of heat. Effective cooling mechanisms are necessary to maintain the integrity of the propulsion system. Fuel management is another critical aspect. Antimatter must be stored safely until needed. Precision in injecting antimatter into the reaction chamber is vital for controlled propulsion. Direct annihilation propulsion could dramatically reduce travel time in space. Missions that currently take months could be completed in weeks. This speed is crucial for deep space exploration. The potential for high thrust-to-weight ratios is a significant advantage. This allows for greater payload capacities. Larger missions and more extensive equipment can be transported. The concept also opens up possibilities for interstellar travel. The efficiency and speed could make reaching nearby star systems feasible. This represents a significant step forward for humanity. Public and private sectors are investing in this technology. Governments and companies see the potential benefits. Funding and resources are being allocated to advance research. Collaboration is key in overcoming the technical challenges. Scientists and engineers from various fields must work together. This interdisciplinary approach is essential for progress. Direct annihilation propulsion represents the future of space travel. Its potential to revolutionize our capabilities is immense. Continued research and innovation will bring us closer to making this concept a reality. Antimatter-catalyzed nuclear pulse propulsion is another innovative approach in space travel. It uses small amounts of antimatter to trigger nuclear reactions. This method combines the principles of nuclear propulsion with the power of antimatter. In this system, antimatter is used as a catalyst. A tiny amount of antimatter initiates a nuclear reaction in a larger mass of conventional nuclear fuel. This enhances the overall energy output. The process begins with the containment of antimatter. When released, antimatter interacts with the nuclear fuel. This interaction results in a controlled nuclear explosion. These controlled explosions generate pulses of high-energy plasma. Magnetic fields direct the plasma out of the propulsion chamber. This expulsion creates thrust, pushing the spacecraft forward. One of the key benefits is increased efficiency. Using antimatter as a catalyst reduces the amount of nuclear fuel needed. This makes the propulsion system lighter and more efficient. The system can produce significant thrust. The energy from each pulse propels the spacecraft at high speeds. This is ideal for long-distance space missions. Safety and control are major considerations. Each nuclear pulse must be precisely timed and contained. Advanced engineering ensures that the process remains stable and controlled. Cooling systems are crucial in this setup. The repeated nuclear pulses generate intense heat. Effective cooling mechanisms are necessary to protect the propulsion system. The potential for scalability is another advantage. The amount of antimatter and nuclear fuel can be adjusted based on mission requirements. This flexibility makes the system adaptable for various missions. Antimatter-catalyzed nuclear pulse propulsion could reduce travel time to distant planets. Faster travel means more feasible human missions to Mars and beyond. This opens up new possibilities for exploration. The concept also holds promise for deep space probes. Unmanned missions to the outer solar system could benefit from the high thrust and efficiency. This could enhance our understanding of distant celestial bodies. International collaboration is vital for developing this technology. Sharing knowledge and resources accelerates progress. Joint efforts can overcome the technical challenges more effectively. Funding and investment are key drivers. Governments and private entities recognize the potential. Financial support is crucial for advancing research and development. Public interest in antimatter propulsion is growing. The possibilities it presents are exciting and inspire imagination. Educational programs and media coverage help raise awareness. As research continues, the feasibility of antimatter-catalyzed nuclear pulse propulsion becomes clearer. Each breakthrough brings us closer to practical applications. The future of space travel could be revolutionized by this technology. Beam core antimatter rockets represent another advanced concept in space propulsion. This approach uses beams of antimatter to create thrust. It's a highly efficient method that leverages the immense energy potential of antimatter. In a beam core rocket, antimatter is stored in magnetic traps. When needed, it is released and directed into a reaction chamber. Here it collides with matter, producing high-energy particles. These high-energy particles are then directed by magnetic fields. The particles are expelled from the spacecraft, generating thrust. This method can achieve extremely high velocities. One of the main advantages is the efficiency of energy conversion. Beam core rockets convert a large portion of the antimatter's energy into thrust. This makes them more efficient than many other propulsion systems. Cooling systems are essential to manage the intense heat generated. The high-energy particles produce significant thermal energy. Advanced cooling technologies are necessary to maintain system integrity. Shielding is also critical. The particles generated are highly energetic and pose radiation risks. Effective shielding protects both the spacecraft and its occupants from radiation. Beam core rockets can potentially reduce interplanetary travel time significantly. Missions to Mars or beyond could be completed in a fraction of the time. This is crucial for human exploration and colonization of distant planets. Fuel efficiency is another significant benefit. The high energy density of antimatter means less fuel is needed for long missions. This reduces the overall mass and cost of space travel. The technology also opens possibilities for deep space exploration. Probes equipped with beam core rockets could reach distant regions of the solar system faster. This enhances our ability to explore and understand space. Safety protocols are paramount. Handling and storing antimatter safely requires advanced systems. Rigorous safety measures ensure that antimatter is contained and controlled at all times. Research into beam core rockets is ongoing. Scientists are exploring new materials and technologies to improve efficiency and safety. These advancements are key to making this propulsion method viable. International collaboration plays a crucial role. Sharing expertise and resources accelerates the development process. Collaborative efforts help overcome the technical challenges more effectively. Funding and investment are driving innovation. Both public and private sectors recognize the potential of beam core rockets. Financial support is essential for continued research and development. Public awareness and interest are growing. The potential of antimatter propulsion captures the imagination. Educational programs and media coverage are helping to inform and inspire the public. As we advance, beam core antimatter rockets could revolutionize space travel. Each technological breakthrough brings us closer to practical applications. The future of space exploration holds exciting possibilities with this propulsion method. Theoretical efficiency and speed of antimatter propulsion are groundbreaking. Antimatter reactions convert almost all mass into energy, unlike chemical or nuclear fuels. This results in unprecedented efficiency levels. The energy yield from antimatter is immense. 1 gram of antimatter can produce energy equivalent to 21 kilotons of TNT. This energy density far surpasses that of conventional fuels. High efficiency translates to higher speeds. Antimatter propulsion could enable spacecraft to reach a significant fraction of the speed of light. This would drastically reduce travel times to distant planets. Such speeds are crucial for interstellar travel. Current propulsion methods would take thousands of years to reach even the nearest star systems. Antimatter propulsion could reduce this to mere decades. For interplanetary missions, the benefits are equally significant. Travel to Mars could be shortened from months to weeks. This makes manned missions more feasible and less taxing on astronauts. Theoretically, speeds approaching 50% of the speed of light are possible. Achieving this would revolutionize our understanding and capability in space exploration. Missions to outer planets and beyond become more practical. Fuel efficiency is also dramatically improved. Antimatter's high energy density means less fuel is required for long missions. This reduces the spacecraft's overall mass and launch costs. The efficiency of antimatter propulsion extends mission lifespans. Spacecraft can carry more scientific instruments and supplies. This enhances the scope and duration of exploratory missions. Higher speeds enable quicker data return from deep space probes. Faster travel means shorter communication delays. This is vital for timely scientific analysis and decision-making. Advanced cooling and shielding systems are necessary. The high energy and speeds generate significant heat and radiation. These systems ensure the spacecraft's components remain functional and safe. Efficiency in antimatter propulsion also impacts mission flexibility. Spacecraft can change trajectories and speeds more readily. This allows for more complex and ambitious mission designs. Theoretical models guide current research. Simulations and experiments aim to validate these models. Each step forward brings us closer to realizing antimatter propulsion's potential. International cooperation accelerates progress. Sharing knowledge and technology helps overcome technical barriers. Global partnerships are crucial in turning theoretical efficiency into practical reality. Public and private investments are essential. Funding supports the development of necessary technologies. Continued investment ensures that research can progress uninterrupted. The promise of antimatter propulsion inspires future generations. The potential to explore the stars drives innovation and ambition. Each discovery brings humanity closer to a new era of space exploration. The current state of antimatter production is highly experimental. Antimatter is primarily produced in particle accelerators, such as the Large Hadron Collider. These facilities create antimatter by accelerating particles to near light speeds and colliding them. Production rates are extremely low. Despite significant advancements, only minute quantities of antimatter can be produced. For example, CERN can produce just a few nanograms of antimatter annually. The cost of production is prohibitively high. Creating a single gram of antimatter would cost trillions of dollars with current technology. This makes large-scale production unfeasible at present. Storing antimatter remains a significant challenge. Magnetic traps are used to contain antimatter particles. These traps prevent antimatter from coming into contact with matter and annihilating. Efficiency in production is a major focus of research. Scientists are exploring new methods to increase yield and reduce costs. Innovations in particle accelerator technology are critical to these efforts. One promising approach is laser-based production. High-powered lasers might offer a more efficient means of generating antimatter. This method is still in the experimental stages, but shows potential. Another avenue is cosmic ray harvesting. Cosmic rays naturally produce antimatter in the upper atmosphere. Capturing this antimatter could provide an alternative production method. International collaboration is essential. Large-scale experiments and facilities are often funded and operated by multiple countries. Shared resources and expertise drive progress in antimatter research. Safety protocols are paramount. Handling and storing antimatter safely requires advanced systems and rigorous procedures. Ensuring the safety of researchers and facilities is a top priority. Research institutions are leading the way. CERN, Fermilab, and other major facilities are at the forefront of antimatter production. Their work is crucial for advancing our understanding and capabilities. Private sector involvement is growing. Companies are beginning to invest in antimatter research, seeing its potential. Public-private partnerships could accelerate technological advancements. Funding remains a significant barrier. The high costs associated with antimatter production necessitate substantial investment. Government and private funding are both critical to ongoing research. Technological breakthroughs are needed. Advances in materials science, particle physics, and engineering are all crucial. Each breakthrough brings us closer to practical antimatter applications. Educational programs are helping to raise awareness. Universities and research institutions are training the next generation of scientists. This education is vital for sustaining progress in the field. Public interest is increasing. The potential of antimatter as an energy source captures the imagination. Media coverage and public outreach are helping to build support for further research. The future of antimatter holds promise. Continued research and investment will eventually overcome current limitations. The goal is to make antimatter a viable energy source for revolutionary applications. Storage and containment technologies for antimatter are highly specialized. The primary challenge is preventing antimatter from coming into contact with matter. Even the slightest contact results in annihilation and energy release. Magnetic traps are the most common containment method. These traps use powerful magnetic fields to suspend antimatter in a vacuum. This prevents it from touching the walls of the container. Penning traps are a specific type of magnetic trap. They combine electric and magnetic fields to create a stable environment for antimatter. These traps are widely used in laboratory settings. Creating a perfect vacuum is essential. Any residual gas or particles can lead to premature annihilation. Advanced vacuum systems are employed to ensure the containment area is free of matter. Temperature control is another critical aspect. Antimatter must be stored at extremely low temperatures to reduce its energy levels. Cryogenic systems are used to maintain these temperatures. The containment systems require constant power. Magnetic fields and cooling systems must be maintained without interruption. This makes antimatter storage energy-intensive. Safety measures are crucial in antimatter containment. Any failure in the system could result in a catastrophic release of energy. Redundant systems and rigorous safety protocols are in place to prevent accidents. Research is ongoing to develop more efficient containment methods. Innovations in magnetic field technology and material science are key areas of focus. These advancements aim to improve stability and reduce costs. One promising development is the use of superconducting magnets. These magnets can generate stronger magnetic fields with less power. This makes them ideal for long-term antimatter containment. Material sciences play a significant role. Developing materials that can withstand the intense conditions of antimatter storage is essential. These materials must be both strong and lightweight. Antimatter containment also involves radiation shielding. The annihilation process produces high-energy gamma rays. Effective shielding is necessary to protect both the containment systems and personnel. Portable containment units are being explored. These units would allow for the transportation of antimatter in small quantities. Such technology could have practical applications in space missions. Collaboration between institutions is vital. Sharing knowledge and technology accelerates the development of advanced containment systems. International efforts are essential for progress in this field. Funding and investment drive innovation. Government grants and private investment support research into better containment technologies. Financial backing is crucial for continued advancements. As technology improves, more efficient and safer containment methods will emerge. These advancements will pave the way for practical applications of antimatter. The future of antimatter storage and containment holds great promise for revolutionizing energy and space travel. Safety concerns are paramount in antimatter research. The energy released from antimatter annihilation is immense. Even a small amount can cause significant destruction if not properly contained. Radiation is a major hazard. Antimatter annihilation produces high-energy gamma rays. These gamma rays can penetrate most materials, posing a serious risk to both humans and equipment. Effective radiation shielding is essential. Traditional materials like lead are used, but they add significant weight. Research is ongoing into lighter, more effective shielding materials. Advanced composites and layered materials are being explored. These materials aim to block or absorb gamma rays more efficiently. They must also withstand the intense heat generated during annihilation. Safety protocols must be rigorously followed. Handling antimatter requires precision and care. Any breach in protocol can lead to catastrophic outcomes. Automated systems enhance safety. Robots and automated handling systems reduce the risk to human operators. These systems can perform precise tasks without human intervention. Containment failure is a critical concern. Redundant systems are in place to prevent such failures. These include backup power supplies and emergency containment fields. Emergency protocols are well defined. In case of containment failure, immediate measures are taken to secure the area. These protocols are regularly reviewed and updated. Training is crucial for personnel. Researchers and technicians must undergo extensive training. They need to understand the risks and the safety measures in place. Safety audits are conducted regularly. These audits ensure that all safety measures are up to date and effective. Continuous improvement is a key aspect of safety management. Radiation monitoring is continuous. Sensors detect any increase in radiation levels. Early detection allows for swift action to mitigate risks. Personal protective equipment is mandatory. Researchers working with antimatter must wear specialized gear. This gear includes radiation suits and shielding devices. Public safety is also considered. Research facilities are located away from populated areas. Strict regulations govern the transportation of antimatter. International guidelines standardize safety practices. Countries working with antimatter follow these guidelines. This ensures a consistent approach to safety worldwide. Advancements in safety technology continue to evolve. As our understanding of antimatter grows, so do our safety measures. Ongoing research aims to make antimatter handling as safe as possible. The cost of antimatter production is extraordinarily high. Current technology makes antimatter one of the most expensive substances in existence. The price tag for producing just 1 gram of antimatter is estimated in the trillions of dollars. The primary expense comes from the energy requirements. Particle accelerators, which are necessary for antimatter production, consume vast amounts of electricity. This energy consumption translates directly into high operational costs. Infrastructure costs are also significant. Building and maintaining particle accelerators require massive investments. Facilities like CERN are billion-dollar enterprises with ongoing maintenance expenses. Raw materials and component costs add to the total. The specialized equipment used in antimatter production, such as superconducting magnets and advanced sensors, is costly to produce and maintain. These components must be of the highest quality to ensure safe and efficient operation. Labor costs cannot be overlooked. Highly skilled scientists and engineers are needed to operate and manage antimatter production facilities. Their expertise commands high salaries, contributing to the overall expense. Research and development expenses are substantial. Continuous innovation is required to improve production efficiency and safety. Funding these R&D efforts involves significant financial resources. Transporting antimatter is another costly aspect. The need for extreme safety measures and specialized containment systems makes transportation complex and expensive. Any transport requires meticulous planning and execution to avoid catastrophic risks. The high cost limits the amount of antimatter produced. Currently, production is measured in nanograms per year, far below what would be needed for practical applications. Scaling up production to useful quantities remains a financial and technological challenge. Government funding plays a crucial role. National and international grants help sustain antimatter research. However, the scale of funding needed often exceeds what public institutions can provide alone. Private investment is becoming increasingly important. Companies see the potential of antimatter as a future energy source and are beginning to invest in research. These investments are critical for advancing the field. Collaborative funding models are being explored. Partnerships between governments, private companies, and academic institutions can pool resources. This collaborative approach helps distribute the financial burden and accelerates progress. Cost reduction strategies are a major focus. Researchers are looking into more efficient production methods and cheaper materials. Breakthroughs in these areas could significantly lower production costs. Energy efficiency improvements are particularly promising. Advances in particle accelerator technology aim to reduce the amount of electricity required. More efficient accelerators could cut down one of the biggest expenses in antimatter production. Long-term investments are needed for sustained progress. Developing antimatter technology to a practical level will require continuous funding over many years. Patience and persistence are key to overcoming the financial hurdles. Despite the high costs, the potential benefits of antimatter make it a worthwhile investment. As technology advances and costs come down, antimatter could revolutionize energy production and space travel. The journey is expensive, but the destination holds incredible promise. Scaling up antimatter production for practical use presents significant challenges. The current production rates are far too low to meet the demands of practical applications. Increasing these rates requires major advancements in technology and infrastructure. One approach to scaling up involves improving particle accelerator efficiency. Modern accelerators need to become more energy efficient and cost-effective. Innovations in accelerator design and operation could lead to higher yields of antimatter. Developing new methods of antimatter production is also essential. Researchers are exploring alternative techniques, such as laser-based production. These methods might offer more efficient ways to generate larger quantities of antimatter. Another focus is on improving antimatter storage. Efficient storage solutions are necessary to handle larger amounts of antimatter safely. Advanced magnetic and cryogenic systems are being developed to meet these needs. Collaboration is key to scaling up production. International partnerships can pool resources and expertise. Joint efforts between countries and institutions are crucial for making significant progress. Investing in infrastructure is vital. Building new facilities and upgrading existing ones will support increased production. This requires substantial financial commitments from both public and private sectors. Government policies and funding play a significant role. Supportive policies and increased funding can drive research and development. Governments must recognize the potential benefits of antimatter and invest accordingly. Private sector involvement is growing. Companies are starting to see the potential commercial applications of antimatter. Their investments are critical for advancing production capabilities. Public awareness and support can influence funding. Educating the public about the potential of antimatter can generate enthusiasm and backing. Increased public support can lead to more funding and resources. Addressing safety concerns is paramount. Larger production volumes mean higher risks. Developing robust safety protocols and technologies is essential to protect both people and facilities. Economic feasibility is a major consideration. The costs of scaling up production must be balanced against the potential benefits. Economies of scale and technological advancements can help make antimatter production more viable. Research into reducing production costs is ongoing. Scientists are working on ways to lower the expenses associated with antimatter generation. Finding cost-effective solutions is crucial for practical use. Long-term commitment is necessary. Scaling up antimatter production will not happen overnight. Sustained investment and research over many years are required to achieve practical levels of production. The potential applications of scaled-up antimatter production are vast. From space travel to energy generation, the possibilities are exciting. Realizing these applications depends on overcoming the current production challenges. As we advance, the goal of practical antimatter use comes closer. Each breakthrough brings new opportunities and possibilities. The journey to scale up production is challenging, but the rewards could be transformative. Chemical rockets have been the backbone of space travel for decades. They rely on the combustion of propellants to produce thrust. This technology has enabled humanity to reach the moon and explore our solar system. The basic principle of chemical rockets involves the burning of fuel and an oxidizer. This combustion generates high-pressure gases. These gases are expelled through a nozzle to produce thrust. Chemical rockets are divided into two main types: liquid and solid rockets. Liquid rockets use liquid propellants, while solid rockets use solid mixtures. Each type has its own advantages and applications. Liquid rockets offer greater control over thrust. They can be throttled, shut down, and restarted. This makes them ideal for missions that require precise maneuvers. Solid rockets, on the other hand, are simpler and more reliable. Once ignited, they burn until all the propellant is consumed. They are often used for booster stages and military applications. The efficiency of chemical rockets is measured by specific impulse. Specific impulse is the thrust produced per unit of propellant consumed. While chemical rockets are efficient, their specific impulse is lower than advanced propulsion methods like antimatter. One of the main limitations of chemical rockets is their fuel requirement. To achieve high speeds, large amounts of fuel are needed. This adds significant weight and complexity to space missions. Despite these limitations, chemical rockets are proven technology. They have a long track record of success in launching satellites, crewed missions, and interplanetary probes. Their reliability makes them the current standard for space travel. The development of reusable rockets has revolutionized the industry. Companies like SpaceX have demonstrated that rockets can be launched, landed, and reused. This reduces costs and increases the frequency of launches. Chemical rockets also play a role in future space exploration. They will likely be used for initial stages of missions, launching payloads into orbit. More advanced propulsion systems can then take over for deep space travel. Research continues to improve chemical rocket technology. New materials and propellant formulations are being developed. These advancements aim to increase efficiency and reduce costs. Environmental concerns are driving innovation as well. The impact of rocket launches on the atmosphere is being studied. Sustainable propellants and cleaner technologies are being explored to mitigate these effects. International collaboration is key in the advancement of chemical rocket technology. Countries share knowledge and resources to push the boundaries of what is possible. This cooperation benefits the global space community. While chemical rockets may eventually be surpassed by more advanced propulsion systems, they remain essential. Their reliability, simplicity, and proven track record ensure they will continue to play a crucial role in space exploration. The future of space travel will likely involve a combination of technologies: chemical rockets for launch, advanced propulsion for travel, and innovative solutions for sustainability. This integrated approach will help humanity reach further into the cosmos. Nuclear thermal propulsion represents a significant advancement in space travel technology. It uses a nuclear reactor to heat a propellant, usually hydrogen. The heated propellant expands and is expelled to produce thrust. The efficiency of nuclear thermal propulsion is higher than that of chemical rockets. This efficiency is measured in terms of specific impulse. Nuclear thermal rockets have a specific impulse roughly twice that of chemical rockets. The basic design involves a nuclear reactor core. This core heats the propellant as it passes through. The heated propellant then exits through a nozzle, creating thrust. One major advantage is the reduced fuel requirement. Because of their higher efficiency, nuclear thermal rockets need less propellant for a given mission. This reduces the overall mass and cost of the spacecraft. Nuclear thermal propulsion can significantly shorten travel times. Missions to Mars, for instance, could be completed in a matter of months. This makes human missions to distant planets more feasible. Safety is a critical concern with nuclear propulsion. Shielding and containment of the reactor are essential. Robust safety measures are in place to protect both the spacecraft and its crew. Development of nuclear thermal propulsion has a long history. Projects like NASA's NERVA program in the 1960s and 70s laid the groundwork. Although the program was cancelled, it provided valuable insights into the technology. Recent interest has revived efforts to develop nuclear thermal propulsion. Modern materials and engineering techniques offer new possibilities. Research is focused on improving reactor efficiency and safety. International collaboration is vital in this field. Countries share expertise and resources to advance nuclear propulsion technology. This global effort accelerates progress and ensures safety standards. Environmental concerns are also considered. The impact of launching and operating a nuclear reactor in space is studied carefully. Efforts are made to minimize any potential harm to Earth's environment. Nuclear thermal propulsion could play a key role in future deep space missions. Its efficiency and reduced travel times are ideal for long-duration missions. This technology could enable human exploration of the outer planets. Funding and political support are crucial. Government and private investment drive the research and development process. Continued support is necessary to bring nuclear thermal propulsion to operational status. Public perception of nuclear technology can influence its development. Education and outreach are important to build understanding and support. Clear communication about safety and benefits helps gain public trust. Advancements in nuclear thermal propulsion open up new possibilities for space exploration. Each breakthrough brings us closer to practical, efficient interplanetary travel. The potential of this technology is immense. As we look to the future, nuclear thermal propulsion could become a cornerstone of space travel. Its advantages in efficiency, speed, and reduced fuel requirements make it a promising option. The journey to develop and deploy this technology continues, with exciting prospects on the horizon. Solar sails offer a unique approach to propulsion by harnessing the power of sunlight. They work by reflecting photons from the sun to create thrust. This method requires no traditional fuel, making it highly efficient for long-term missions. The concept relies on large reflective sails. These sails capture momentum from sunlight, gradually accelerating the spacecraft. Over time, this steady acceleration can achieve significant speeds. One of the main advantages is the absence of fuel weight. Without the need for propellant, spacecraft can be lighter and carry more payload. This makes solar sails ideal for deep space exploration. Deployment of solar sails involves unfurling massive, lightweight sheets. These sheets must be extremely thin and reflective. Materials like mylar and kapton are commonly used for their durability and lightweight. Solar sails operate best in regions with strong sunlight. Near the sun, they can achieve higher accelerations. However, they can still function in the outer solar system, albeit with reduced efficiency. The continuous acceleration provided by solar sails allows for long-duration missions. Unlike traditional rockets, they don't run out of fuel. This makes them suitable for interstellar probes and other long-term projects. Navigating with solar sails requires precise control. By adjusting the angle of the sails, spacecraft can change direction and speed. This maneuverability is crucial for targeting distant destinations. The Japanese spacecraft Ikaros successfully demonstrated solar sail technology in 2010. It deployed a large sail and used sunlight for propulsion. This mission proved the viability of solar sails for space travel. Future missions plan to use solar sails for more ambitious goals. Concepts like NASA's Sunjammer aim to deploy even larger sails. These projects seek to explore the potential of solar sails for reaching farther into space. Solar sails offer a silent, vibration-free mode of travel. Without engines or fuel combustion, they provide a smooth journey. This can be advantageous for delicate scientific instruments and long-term operations. One challenge is the initial deployment in space. Sails must be packed tightly and then unfurled without damage. Advanced engineering ensures they deploy smoothly and effectively. Environmental impacts are minimal compared to traditional propulsion. Solar sails produce no emissions or waste. Their reliance on sunlight makes them a clean and sustainable option for space travel. International cooperation enhances solar sail development. Collaborative missions and shared technology advance the field. Global efforts can help overcome technical challenges and improve designs. Funding and research continue to drive innovation in solar sails. Government agencies and private companies invest in this promising technology. Continued support is essential for advancing solar sail capabilities. As technology progresses, solar sails could revolutionize space travel. Their efficiency, sustainability, and long-term potential make them a key component of future exploration. The journey to perfect solar sail technology continues, with exciting developments on the horizon. Ion propulsion represents a cutting-edge technology for space travel. It uses electric fields to accelerate ions and produce thrust. This method is highly efficient compared to traditional chemical rockets. The core of ion propulsion is the ion thruster. It ionizes a propellant, usually xenon, by stripping electrons from atoms. The resulting ions are then accelerated through an electric field. The efficiency of ion propulsion is measured by its specific impulse. Ion thrusters have a much higher specific impulse than chemical rockets. This means they can achieve greater speeds with less propellant. One major advantage is the prolonged thrust capability. Ion thrusters can operate for extended periods, gradually increasing the spacecraft's velocity. This makes them ideal for long-duration missions. The Deep Space One mission successfully demonstrated ion propulsion. It used an ion thruster to navigate and conduct scientific experiments. This mission proved the practicality of ion propulsion for deep space travel. Ion propulsion is also used on the Dawn spacecraft. Dawn explored the asteroid belt, visiting Vesta and Ceres. Its ion thrusters allowed it to change orbits and conduct detailed studies. The main drawback of ion propulsion is its low thrust output. While it provides continuous thrust, the acceleration is slow. This makes ion thrusters less suitable for rapid maneuvers or launch stages. Despite this, ion propulsion is perfect for missions requiring efficiency over speed. Its ability to maintain thrust for long periods enables it to reach high velocities. This is crucial for missions to distant destinations. Ion thrusters are highly efficient in terms of fuel consumption. The ionization process and electric acceleration use far less propellant. This reduces the overall mass of the spacecraft. Power sources for ion thrusters typically include solar panels. These panels generate the electricity needed for ionization and acceleration. Advanced missions might use nuclear power for greater energy output. The technology continues to evolve. Researchers are developing more powerful and efficient ion thrusters. Innovations in materials and engineering improve their performance and reliability. The environmental impact of ion propulsion is minimal. It produces no chemical emissions or pollutants. This makes it a cleaner alternative to traditional propulsion methods. International collaboration is key to advancing ion propulsion. Shared research and joint missions enhance technological development. Global cooperation ensures that the benefits of ion propulsion are realized. Funding and investment drive innovation in this field. Both governmental and private sector support are essential. Continued investment will lead to more advanced and capable ion propulsion systems. Ion propulsion is set to play a major role in the future of space exploration. Its efficiency and sustainability make it a valuable technology for reaching distant targets. As development progresses, ion propulsion will unlock new possibilities for space travel. Fusion propulsion is an exciting prospect for the future of space travel. It harnesses the power of nuclear fusion, the same process that powers the sun. This method promises significant advancements in speed and efficiency. The basic principle involves fusing atomic nuclei to release energy. Hydrogen isotopes like deuterium and tritium are commonly used. When these nuclei fuse, they release an immense amount of energy. Fusion propulsion offers a much higher specific impulse than chemical or even nuclear thermal rockets. This means that spacecraft can travel faster and farther on the same amount of fuel. The potential for interstellar travel becomes more feasible with fusion propulsion. One of the main challenges is achieving and maintaining the high temperatures needed for fusion. Temperatures must reach millions of degrees. Advanced containment methods, such as magnetic confinement, are required to handle these conditions. Magnetic confinement uses powerful magnetic fields to contain the hot plasma. This prevents the plasma from coming into contact with the walls of the reactor. Maintaining stable confinement is a critical technical challenge. Another approach is inertial confinement, which uses lasers or ion beams to compress the fuel. This method involves rapidly heating and compressing the fuel to achieve fusion conditions. Both approaches are currently being explored and developed. The energy released from fusion reactions can be converted into thrust. This can be done using magnetic nozzles or direct energy conversion methods. Efficiently harnessing this energy is key to practical fusion propulsion systems. Fusion propulsion has the potential to drastically reduce travel times within the solar system. Missions to Mars could be completed in weeks instead of months. This would greatly enhance our capability for manned missions to other planets. The long-term goal is to enable interstellar travel. Fusion propulsion could make it possible to reach nearby star systems within a human lifetime. This opens up new possibilities for exploration and even colonization. Safety is a major consideration in developing fusion propulsion. Containing and controlling the fusion reaction safely is paramount. Advanced engineering and robust safety protocols are essential. Funding and research are crucial to overcoming the technical challenges. Government and private sector investments drive progress in fusion technology. Continued support is needed to bring fusion propulsion from theory to reality. International collaboration accelerates development. Sharing knowledge and resources among countries enhances technological advancement. Joint efforts are crucial for tackling the complexities of fusion propulsion. Environmental benefits are significant. Fusion produces minimal radioactive waste compared to fission. It also avoids the chemical emissions associated with traditional rocket fuels. Public interest in fusion propulsion is growing. The potential for revolutionary space travel captures the imagination. Education and outreach help build support for ongoing research. As technology advances, fusion propulsion could transform our approach to space exploration. Its efficiency and capability offer a glimpse into the future of interplanetary and interstellar missions. The journey to develop and implement fusion propulsion continues with promising prospects ahead. Drastically reduced travel time is one of the most exciting prospects of advanced propulsion systems. Current technology requires months or even years to reach distant planets. New propulsion methods could shorten these journeys significantly. For instance, antimatter propulsion has the potential to cut travel time to Mars from months to weeks. This is a game changer for manned missions, reducing the time astronauts spend in space. Shorter trips also mean fewer resources are needed, lowering mission costs. Fusion propulsion could further reduce travel times. With its high efficiency and powerful thrust, fusion rockets might reach Mars in just a few weeks. This rapid transit makes regular trips to the red planet more feasible. Interstellar travel is another frontier where reduced travel time is crucial. With conventional propulsion, reaching even the closest stars would take thousands of years. Advanced propulsion could make these journeys possible within a human lifetime. Ion propulsion also offers significant time savings for certain missions. While its acceleration is slow, the continuous thrust can achieve high speeds over long distances. This is ideal for deep space probes that need to travel vast distances efficiently. Solar sails provide a unique advantage by continuously accelerating as they capture solar energy. Over time, they can reach high speeds, reducing travel times for missions to the outer solar system. Their fuel-free operation further enhances their efficiency for long-duration voyages. Nuclear thermal propulsion can halve the time required for interplanetary missions. Its high thrust and efficiency are suited for crewed missions to Mars and beyond. Faster travel times reduce the risks associated with long-duration spaceflight. Reduced travel time is not just about speed. It's also about increasing mission flexibility. Faster transit allows for more dynamic mission planning and quicker responses to new opportunities or challenges. Shorter travel times improve the safety and well-being of astronauts. Prolonged exposure to microgravity and space radiation poses significant health risks. Minimizing time spent in space mitigates these dangers. Faster journeys also mean quicker data return for scientific missions. Probes can reach their destinations sooner, sending back valuable information faster. This accelerates our understanding of distant worlds and phenomena. Cost efficiency is another benefit. Reduced travel time lowers the need for extensive life support systems and supplies. This can significantly cut the overall expense of space missions. Public interest and support often hinge on mission duration. Shorter, more frequent missions keep public engagement high. This can drive funding and support for future exploration endeavors. Technological advancements continue to push the boundaries of what's possible. Each breakthrough in propulsion technology brings us closer to reducing travel times even further. Ongoing research and development are essential for realizing these goals. International cooperation can accelerate progress. Shared efforts and resources make developing and deploying advanced propulsion systems more feasible. Collaborative missions benefit from diverse expertise and funding sources. The promise of drastically reduced travel time energizes the space exploration community. It opens new possibilities for human and robotic missions. As technology advances, the dream of swift, efficient space travel moves closer to reality. Greater payload capacity is another significant advantage of advanced propulsion systems. Traditional rockets are limited by the weight of the fuel they must carry. More efficient propulsion methods can reduce this burden, allowing for larger payloads. With antimatter propulsion, the incredible energy density means less fuel is needed. This frees up space and weight for additional scientific instruments, equipment, or supplies. Missions can be more ambitious and comprehensive. Fusion propulsion offers similar benefits. The high energy output of fusion reactions allows for a smaller fuel mass. This increases the spacecraft's capacity to carry heavier payloads without compromising performance. Ion propulsion systems, while providing continuous thrust, also enable greater payload capacities. Their efficiency in fuel consumption means less propellant is required. This makes them ideal for long-duration missions with substantial payload needs. Nuclear thermal propulsion can also enhance payload capabilities. By providing a higher thrust-to-weight ratio, it allows spacecraft to carry more. This is crucial for manned missions, which require extensive life support systems and equipment. Solar sails using sunlight for propulsion eliminate the need for traditional fuel. This creates more room for scientific instruments and cargo. Their continuous acceleration also supports larger payloads over long distances. Greater payload capacity directly impacts mission flexibility. More instruments and equipment mean more extensive scientific research. Missions can achieve broader objectives and gather more data. For manned missions, increased payload capacity is vital. It allows for more robust life support systems, additional crew amenities, and more scientific experiments. This improves the overall mission safety and success rate. Space colonization efforts also benefit from greater payload capacity. Transporting habitat modules, supplies, and construction materials requires significant lift capability. Advanced propulsion makes these large-scale missions more feasible. Increased payload capacity supports the deployment of more sophisticated technology. Larger telescopes, deeper space probes, and advanced robotics can be sent on missions. This enhances our ability to explore and understand the universe. Economic benefits are notable as well. More efficient missions with greater payloads reduce the cost per kilogram of cargo. This makes space exploration more cost-effective and accessible. Greater payloads also support commercial endeavors. Satellite deployment, space tourism, and resource extraction all benefit from enhanced lift capabilities. This opens new business opportunities in space. Research and development continue to improve payload capacities. Innovations in materials, science, propulsion efficiency, and spacecraft design contribute to this progress. Each advancement brings us closer to realizing the full potential of space travel. International collaboration enhances payload capacity development. Shared knowledge and resources lead to better designs and more powerful propulsion systems. Joint missions can carry larger, more complex payloads. The promise of greater payload capacity drives excitement in the space community. It expands the possibilities for exploration, research, and commercial activities. As technology evolves, the potential for carrying larger payloads will continue to grow. Deep space exploration possibilities are greatly expanded by advanced propulsion systems. Faster travel times and greater payload capacities enable missions to reach farther destinations. This opens new frontiers for scientific discovery and exploration. Advanced propulsion technologies make missions to the outer planets more feasible. Probes can be sent to explore the moons of Jupiter and Saturn in greater detail. These missions can provide insights into the potential for life and the history of our solar system. Beyond the outer planets, advanced propulsion can take us to the Kuiper Belt and beyond. This region is home to many icy bodies that hold clues to the solar system's formation. Exploring these distant objects can deepen our understanding of planetary science. Interstellar probes become a possibility with advanced propulsion. Missions to nearby star systems, such as Alpha Centauri, could become a reality. These missions could search for exoplanets and study their potential for habitability. Long-duration missions to explore the outer reaches of the solar system can carry more advanced instruments. These missions can gather more comprehensive data on distant celestial bodies. Enhanced payload capacities support sophisticated scientific equipment. Astrobiology missions benefit from advanced propulsion. Faster travel times allow probes to reach and study potentially habitable moons and planets. This could significantly advance our search for extraterrestrial life. Advanced propulsion enables detailed exploration of asteroid belts. Missions can investigate multiple asteroids, providing a broader understanding of these bodies. This information is crucial for both science and planetary defense. Deep space telescopes can be deployed to more distant orbits. This reduces interference from Earth's atmosphere and other celestial bodies. These telescopes can provide clearer and more detailed observations of the universe. Sample return missions become more feasible with advanced propulsion. Missions can collect samples from distant moons, asteroids, or even other planets and return them to Earth. This direct analysis can yield invaluable scientific data. Advanced propulsion supports missions to study the heliosphere and interstellar space. Probes can travel beyond the influence of the solar wind, providing new data on the boundary of our solar system. This enhances our understanding of the space environment. Exploring the Oort cloud is another possibility. This distant region is thought to be a reservoir of comets. Missions to the Oort cloud could reveal more about the outermost reaches of our solar system. Increased payload capacities support the deployment of advanced robotics. Robotic explorers can be sent to distant worlds to conduct detailed studies. These robots can operate in environments that are challenging for human astronauts. Collaboration on deep space missions is enhanced by advanced propulsion. International partnerships can pool resources and expertise to achieve more ambitious goals. This cooperative approach maximizes the scientific return on investment. The potential for discovering new phenomena is vast. Advanced propulsion allows us to investigate regions of space that were previously out of reach. Each mission can unveil new aspects of the universe, leading to groundbreaking discoveries. The future of deep space exploration is bright with advanced propulsion. These technologies open new possibilities for scientific research and discovery. As we continue to innovate, the boundaries of exploration will keep expanding, revealing more of the cosmos. Colonization of distant planets is a bold and ambitious goal enabled by advanced propulsion systems. Faster travel times make it possible to send larger crews and supplies. This is essential for establishing sustainable human settlements. The Moon and Mars are prime candidates for early colonization. Proximity and relatively hospitable conditions make them ideal starting points. Advanced propulsion reduces the travel time, making regular trips more feasible. Larger payload capacities allow for transporting essential infrastructure. Habitats, life support systems, and scientific equipment can be delivered more efficiently. This is crucial for building self-sufficient colonies. On Mars, advanced propulsion supports the delivery of construction materials. Building durable habitats to protect colonists from harsh conditions is a priority. Efficient transport of these materials is vital for long-term survival. Colonization efforts also benefit from increased safety and redundancy. Faster travel times mean emergency supplies can be sent quickly if needed. This enhances the overall resilience of the colonies. Establishing agriculture on distant planets is another possibility. Transporting agricultural equipment and seeds is easier with greater payloads. Sustainable food production is key to long-term colonization success. Water extraction and management are critical for colonization. Advanced propulsion can deliver the necessary technology to locate and utilize water sources. This supports both human needs and agricultural efforts. Energy production infrastructure can also be transported. Solar panels, nuclear reactors, and other power sources are essential. Reliable energy is necessary for maintaining habitats and supporting daily activities. Research stations can be established to study the local environment. Understanding the geology, climate, and potential resources of the new planet is crucial. These stations pave the way for broader colonization efforts. Advanced propulsion enables regular supply missions to maintain colonies. Consistent delivery of essentials and new technology supports colony growth and stability. This is key to transforming temporary outposts into permanent settlements. International collaboration is vital for successful colonization. Joint missions share the financial and technological burden. Collaborative efforts increase the chances of success and sustainability. Colonization also offers opportunities for scientific research. Living on another planet provides unique insights into human physiology and adaptation. This research is valuable for future space exploration. Robotic assistance plays a significant role in early colonization. Robots can prepare habitats, mine resources, and perform maintenance tasks. This reduces the workload on human settlers and enhances safety. Public support and interest in colonization are growing. The idea of living on another planet captures the imagination. Educational programs and media coverage help build enthusiasm and backing. The ultimate goal of colonizing distant planets is to ensure humanity's long-term survival. Advanced propulsion systems make this ambitious vision more attainable. As technology continues to advance, the dream of interplanetary colonization moves closer to reality. Implications for interstellar travel are profound with the advent of advanced propulsion systems. These technologies make the dream of reaching star systems more attainable. The possibility of exploring planets around other stars becomes more realistic. Antimatter propulsion offers the potential for achieving a significant fraction of the speed of light. This could reduce travel time to nearby star systems from millennia to mere decades. The vast distances of interstellar space become less daunting. Fusion propulsion also holds promise for interstellar journeys. The immense energy released from fusion reactions can propel spacecraft at unprecedented speeds. Missions to stars like Proxima Centauri become feasible within a human lifetime. Interstellar travel requires long-term sustainability. Advanced propulsion systems enable larger payloads, which include habitats and life support systems. This is crucial for maintaining crews on extended missions. Exploring exoplanets is a primary goal of interstellar travel. With advanced propulsion, we can send probes to study these distant worlds up close. Detailed observations can reveal their atmospheres, climates, and potential for life. Communication over interstellar distances is a significant challenge. Advanced propulsion reduces the time delay in transmitting data back to Earth. Faster travel means quicker access to valuable scientific information. Interstellar missions could also involve autonomous spacecraft. These vessels would need to operate independently for long periods. Advanced propulsion systems support the energy requirements of such autonomous operations. Robust shielding is necessary for interstellar journeys. Spacecraft must be protected from cosmic radiation and micrometeoroids. Advanced propulsion systems can help achieve the necessary velocity to minimize exposure time. The search for extraterrestrial intelligence is another exciting prospect. Faster travel allows us to reach and investigate signals from distant civilizations. This could potentially lead to groundbreaking discoveries. International cooperation is essential for interstellar missions. The resources and expertise required are immense. Collaborative efforts enhance the feasibility and success of these ambitious projects. Public interest in interstellar travel drives support and funding. The allure of exploring other star systems captures the human imagination. Media and educational outreach help sustain enthusiasm and investment. Interstellar travel has profound philosophical implications. It challenges our understanding of humanity's place in the universe. The potential to encounter other forms of life raises significant ethical and existential questions. Technological spin-offs from interstellar research benefit many fields. Advances in material science, energy production, and life support systems have broad applications. These innovations can improve life on Earth. The pursuit of interstellar travel inspires future generations. It encourages young people to pursue careers in science, technology, engineering, and mathematics. This drive is essential for continued progress in space exploration. As we continue to develop advanced propulsion systems, the dream of interstellar travel moves closer to reality. The implications for science, technology, and humanity are vast. Each step forward brings us nearer to exploring the stars. Antimatter containment failures pose serious risks. The energy released from even a small amount of antimatter can be catastrophic. Ensuring safe containment is critical for any application of antimatter technology. Containment systems rely on magnetic and electric fields to isolate antimatter. If these fields fail, antimatter can come into contact with matter. This results in an explosive release of energy. Magnetic traps, such as penning traps, are commonly used. They must operate flawlessly to prevent containment breaches. Any disruption in power or magnetic field stability can lead to failure. Temperature control is vital for containment. Antimatter needs to be stored at extremely low temperatures. Failure in cryogenic systems can compromise containment integrity. Backup systems are essential. Redundant power supplies and magnetic field generators provide a safety net. These systems must be regularly tested and maintained. Safety protocols must be rigorously followed. Handling and transporting antimatter require meticulous procedures. Any lapse can increase the risk of containment failure. Automated systems enhance safety. Robots and automated mechanisms reduce human interaction with antimatter. This minimizes the risk of accidental breaches. Containment facilities must be designed with fail-safes. In case of a breach, immediate measures to isolate and contain the explosion are necessary. This includes advanced shielding and emergency shutdown procedures. Training is crucial for personnel. Researchers and technicians must be thoroughly trained in antimatter safety. They need to understand the protocols and the importance of strict adherence. Regular safety audits are necessary. These audits ensure all systems and protocols are up to date. Continuous improvement in safety measures is essential to mitigate risks. Research into new containment methods is ongoing. Innovations in magnetic field technology and materials science aim to enhance safety. These advancements could lead to more robust containment systems. International collaboration on safety standards is vital. Shared knowledge and best practices improve global safety and antimatter research. Consistent standards ensure a high level of safety worldwide. Public perception of antimatter technology depends on safety assurances. Transparent communication about safety measures builds trust. It's important to address public concerns with clear and accurate information. Funding for safety research is essential. Governments and private sectors must invest in developing safer containment methods. This funding supports the necessary research and innovation. Ultimately, the goal is to make antimatter technology as safe as possible. Advances in containment technology will reduce the risk of failures. Safe containment is the foundation for any future use of antimatter in practical applications. Weaponization concerns are a significant issue with antimatter technology. The immense energy potential of antimatter makes it a powerful tool. However, this same potential raises fears about its use in weapons. Even a small amount of antimatter can produce a massive explosion. This makes it far more destructive than conventional explosives. The implications for warfare and global security are profound. Antimatter weapons could surpass the destructive power of nuclear weapons. The energy release from antimatter annihilation is orders of magnitude greater. This level of destruction poses a severe threat to global stability. The development of antimatter weapons could trigger an arms race. Nations may feel compelled to develop their own antimatter arsenals. This escalation increases the risk of conflict and accidental detonations. International regulations are crucial to prevent weaponization. Treaties and agreements must specifically address antimatter. These regulations should ban the development and deployment of antimatter weapons. Verification and enforcement of these treaties are challenging. Advanced detection methods are needed to monitor compliance. International cooperation is essential for effective enforcement. Public awareness and advocacy play a role in prevention. Educating the public about the dangers of antimatter weapons can build support for regulation. Advocacy groups can influence policymakers to prioritize disarmament efforts. Ethical considerations are central to the debate. The use of antimatter as a weapon raises profound moral questions. The potential for catastrophic loss of life and environmental damage must be weighed against any perceived benefits. Scientific communities have a responsibility to address these concerns. Researchers must advocate for peaceful uses of antimatter technology. They should also work to develop safeguards against its misuse. Funding and research should focus on non-military applications. Directing resources towards peaceful uses can mitigate the risk of weaponization. This includes medical, energy, and space exploration applications. Transparency in antimatter research is essential. Open sharing of information reduces the likelihood of secretive weapon development. International collaboration fosters trust and mutual understanding. Education and training programs should emphasize ethical considerations. Future scientists and engineers must be aware of the implications of their work. Ethical training can guide responsible research practices. Legislative action is necessary to establish clear legal frameworks. Laws should define and criminalize the development of antimatter weapons. Robust legal frameworks are a deterrent against potential misuse. Global leadership is needed to address weaponization concerns. Nations must come together to lead by example. Diplomatic efforts can promote a unified stance against the weaponization of antimatter. Ultimately, the focus should be on harnessing antimatter for the betterment of humanity. Responsible stewardship of this powerful technology is crucial. By prioritizing peaceful applications, we can avoid the dangers of weaponization and ensure a safer future. The environmental impact of antimatter production and use is a critical concern. Producing antimatter requires enormous amounts of energy. This energy often comes from conventional power sources, which can have a significant carbon footprint. Efficient antimatter production methods are necessary to minimize environmental harm. Current technologies are energy-intensive and expensive. Advancements in this area are crucial for reducing the overall environmental impact. Containment failures and accidental releases pose additional risks. Antimatter annihilation produces high-energy gamma rays, which can be harmful to the environment. Proper containment and safety measures are essential to prevent such incidents. Space missions utilizing antimatter must consider the potential for environmental damage. Launching and operating spacecraft with antimatter propulsion systems require stringent safety protocols. Ensuring that these missions do not adversely affect space environments is vital. Disposal of antimatter presents unique challenges. Unlike conventional waste, antimatter cannot simply be discarded. Developing safe and effective disposal methods is critical to avoid environmental contamination. Long-term storage of antimatter also raises environmental concerns. The materials and energy required to maintain containment systems have their own environmental impacts. Sustainable practices must be implemented to mitigate these effects. Research into alternative energy sources for antimatter production can help. Renewable energy sources like solar or wind power could reduce the carbon footprint. This approach aligns with global efforts to combat climate change. The potential for antimatter to revolutionize energy production exists. If harnessed safely, antimatter could provide a highly efficient energy source. This could reduce reliance on fossil fuels and decrease greenhouse gas emissions. Environmental regulations must evolve to address antimatter technology. Clear guidelines and standards are needed to ensure environmental protection. Policymakers must work with scientists to develop appropriate regulations. Public awareness and engagement are essential. Educating the public about the environmental impacts of antimatter can drive demand for sustainable practices. Advocacy and activism can influence industry and government actions. The space environment itself can be impacted by antimatter use. High-energy particles from antimatter reactions could affect spacecraft and satellites. Understanding and mitigating these effects are crucial for safe space operations. Antimatter research facilities must adopt green practices. Reducing waste, recycling materials, and using renewable energy sources can lessen environmental impacts. Sustainable research practices benefit both the environment and public perception. Collaboration between environmental scientists and antimatter researchers is vital. Interdisciplinary efforts can identify and address potential environmental risks. This cooperation ensures a balanced approach to technological advancement. Investing in green technologies for antimatter production and use is a forward-thinking approach. It supports long-term sustainability and aligns with global environmental goals. Responsible development of antimatter technology can lead to significant environmental benefits. As antimatter technology advances, its environmental impact must be carefully managed. With proper regulations, sustainable practices, and public engagement, the benefits of antimatter can be realized without compromising the health of our planet. Ethical use in space exploration is a fundamental concern as we advance with antimatter technology. Ensuring that antimatter is used for peaceful purposes is paramount. This involves strict regulations and international agreements to prevent its misuse. The potential for dual-use technology complicates ethical considerations. While antimatter can revolutionize space travel, it also poses significant risks if weaponized. Establishing clear ethical guidelines is essential to navigate these dual-use scenarios. Respect for celestial bodies is another ethical issue. As we explore and potentially colonize other planets and moons, it is crucial to minimize our impact. Preserving the natural state of these environments must be a priority. The potential discovery of extraterrestrial life raises ethical questions. We must ensure that our actions do not harm other life forms or disrupt their ecosystems. This requires careful planning and adherence to planetary protection protocols. Resource utilization in space must be conducted ethically. Extracting resources from asteroids or other celestial bodies should be done sustainably. We must avoid repeating the mistakes of resource exploitation on Earth. The benefits of space exploration should be shared globally. Ethical use involves ensuring that advancements in antimatter technology benefit all of humanity. This includes equitable access to the knowledge and resources gained from space missions. Transparency in antimatter research and missions is vital. Open communication about objectives, methods, and findings builds trust. It also allows for public scrutiny and accountability, ensuring ethical standards are maintained. Informed consent is crucial for space missions involving humans. Astronauts and other personnel must be fully aware of the risks and implications. Their participation should be voluntary and based on comprehensive information. Ethical considerations extend to the long-term impacts of space exploration. We must consider the legacy we leave for future generations. This involves thoughtful decision-making to ensure sustainable and responsible exploration. Collaboration with international partners requires mutual respect and ethical conduct. Joint missions should adhere to agreed-upon ethical standards. This fosters cooperation and ensures that all parties act responsibly. Investing in education and outreach promotes ethical use. By informing the public and future scientists about ethical issues, we build a culture of responsibility. This helps ensure that advancements are made with consideration for their broader impact. Ethical use also involves the fair distribution of resources and opportunities. Developing countries should have the chance to participate in and benefit from space exploration. Inclusivity strengthens the global space community. Addressing ethical issues proactively can prevent conflicts and misunderstandings. Establishing clear guidelines and fostering open dialogue are key strategies. This approach ensures that ethical considerations are integrated into all stages of space exploration. Advancements in antimatter technology must align with our ethical principles. By prioritizing peace, sustainability, and respect for life, we can harness antimatter's potential responsibly. This commitment to ethics will guide us as we explore the final frontier. Ultimately, ethical use in space exploration reflects our values as a society. It challenges us to act with integrity, foresight, and a sense of responsibility. As we venture further into space, these principles will help ensure that our actions benefit all of humanity. International regulations and treaties are crucial for governing the use of antimatter technology. These agreements ensure that antimatter is developed and used responsibly. They help prevent the potential for misuse and weaponization. Existing treaties like the Outer Space Treaty provide a framework. This treaty prohibits the placement of nuclear weapons in space and encourages peaceful exploration. Expanding such treaties to include antimatter is essential. New agreements specifically addressing antimatter are needed. These treaties must outline the permissible uses and establish clear prohibitions. They should promote transparency and cooperation among nations. Verification and enforcement mechanisms are vital. Effective treaties require robust systems to monitor compliance. This includes international inspections and data sharing to ensure adherence to regulations. International cooperation is key to developing these treaties. Countries must work together to create comprehensive and fair regulations. Collaborative efforts can address the complex challenges posed by antimatter technology. Involving international organizations enhances the process. Bodies like the United Nations can facilitate discussions and negotiations. Their involvement lends legitimacy and ensures broad participation. Public engagement and input are important. Including voices from civil society, industry, and academia ensures that treaties are well-rounded. This inclusive approach helps build widespread support and compliance. Updating existing treaties to reflect new technologies is necessary. As antimatter research progresses, treaties must evolve. Regular reviews and updates ensure that regulations remain relevant and effective. Addressing dual-use concerns is a major focus. Treaties should differentiate between peaceful and military applications. Clear guidelines can help prevent the militarization of antimatter technology. Environmental protections should be included. Treaties must consider the potential environmental impacts of antimatter use. This ensures that space exploration does not harm celestial bodies or Earth's environment. Resource utilization in space requires careful regulation. Agreements should govern the extraction and use of space resources. This promotes sustainable practices and prevents conflicts over valuable assets. International treaties can also foster scientific collaboration. By promoting shared research and data, they advance our collective knowledge. This spirit of cooperation benefits all participating nations. Sanctions and penalties for non-compliance are essential. Effective treaties must have consequences for violations. This deters potential breaches and maintains the integrity of the agreements. Education and training programs support treaty implementation. Providing resources and knowledge helps nations comply with regulations. These programs ensure that all countries can participate fully and responsibly. Ultimately, international regulations and treaties safeguard our shared future. They ensure that antimatter technology is developed for the benefit of all humanity. Through cooperation and commitment, we can navigate the challenges and opportunities of this powerful technology. Leading research institutions play a pivotal role in advancing antimatter technology. These organizations conduct groundbreaking research and develop innovative applications. Their work is essential for overcoming the challenges of antimatter production and containment. CERN, the European Organization for Nuclear Research, is at the forefront. Home to the Large Hadron Collider, CERN conducts experiments that produce and study antimatter. Their research provides critical insights into particle physics and antimatter properties. Fermilab in the United States is another key player. Known for its high-energy particle physics research, Fermilab focuses on antimatter production and its potential applications. Their work complements and extends the findings from other major research centers. The SLAC National Accelerator Laboratory also contributes significantly. Located in California, SLAC's research in particle acceleration and high-energy physics is vital. They explore new methods for antimatter generation and containment. In Japan, the High Energy Accelerator Research Organization, KEK, is a leader in the field. KEK conducts advanced research in particle physics, including antimatter studies. Their international collaborations enhance global understanding of antimatter. The Joint Institute for Nuclear Research in Russia is another prominent institution. JINR's work in particle physics and antimatter research is well regarded. They contribute valuable data and technological advancements. In Europe, the Max Planck Institute for Physics is notable. Their research encompasses a broad range of topics in theoretical and experimental physics. This includes significant contributions to antimatter studies. China's Institute of High Energy Physics is making strides as well. IHEP's work in particle physics and accelerator technology is rapidly advancing. They are becoming a key player in the global antimatter research community. University-based research programs also play a crucial role. Institutions like MIT, Stanford, and Oxford have dedicated programs for antimatter research. These universities foster innovation and train the next generation of scientists. National laboratories, such as Lawrence Berkeley National Laboratory, support this effort. Their research in high-energy physics and advanced materials is critical. These labs provide the infrastructure and expertise needed for cutting-edge research. Collaborations between these institutions are essential. Joint projects and shared data accelerate progress and innovation. International partnerships leverage the strengths of each institution for greater impact. Government funding and support are vital for these institutions. National and international grants enable sustained research efforts. This funding is crucial for maintaining and expanding research capabilities. Private sector partnerships enhance research opportunities. Companies invest in antimatter research for potential commercial applications. These collaborations bring additional resources and expertise. Public engagement and outreach by these institutions are important. Educating the public about antimatter research fosters support and interest. Transparent communication about their work builds trust and enthusiasm. Ultimately, the work of leading research institutions drives the field forward. Their discoveries and innovations lay the foundation for the future of antimatter technology. As research progresses, these institutions will continue to be at the heart of scientific advancement. Recent breakthroughs in antimatter research are propelling the field forward. Scientists have made significant advances in production, containment, and application. These developments are bringing us closer to practical uses of antimatter technology. One major breakthrough is in antimatter production efficiency. Researchers have developed new techniques that increase the yield of antimatter particles. This makes production more feasible and cost-effective. Another significant advancement is in containment technology. Improved magnetic traps now allow for longer and more stable storage of antimatter. These developments reduce the risk of accidental annihilation. There have also been breakthroughs in antimatter propulsion concepts. Experimental setups have successfully demonstrated the principles of antimatter propulsion. These experiments pave the way for future spacecraft designs. In the medical field, antimatter is showing promise for cancer treatment. Recent studies have explored using positrons in targeted cancer therapies. This approach could lead to more effective and less invasive treatments. Astrophysics has benefited from antimatter research as well. Discoveries about cosmic rays and antimatter in space are enhancing our understanding of the universe. These findings help explain phenomena such as dark matter and cosmic radiation. Particle physics continues to make strides. Researchers at CERN and other institutions have observed rare antimatter interactions. These observations provide deeper insights into the fundamental laws of physics. Innovations in detection technology are also noteworthy. New detectors can more accurately measure and identify antimatter particles. This improves experimental accuracy and opens up new research possibilities. Collaborative projects have yielded impressive results. International teams have successfully conducted complex experiments that would be difficult for a single institution. These collaborations accelerate progress and share expertise. There have been advancements in theoretical models as well. Improved simulations and mathematical models help predict antimatter behavior. This theoretical work guides experimental research and technological development. Private sector involvement is driving innovation. Companies investing in antimatter research are developing new applications and technologies. Their contributions complement academic and governmental research efforts. Recent breakthroughs in materials science are aiding antimatter research. New materials can better withstand the extreme conditions of antimatter containment. These materials enhance the safety and durability of containment systems. Progress in quantum computing is impacting antimatter research. Quantum simulations can model antimatter interactions more precisely. This helps scientists understand complex behaviors and design better experiments. Public interest and support have grown due to these breakthroughs. Increased awareness and engagement help secure funding and foster a supportive environment. Public enthusiasm drives further research and innovation. Educational initiatives are spreading knowledge about recent discoveries. Universities and research institutions are incorporating the latest findings into their curricula. This ensures that the next generation of scientists is well equipped. The momentum from recent breakthroughs is building. Each discovery and innovation brings us closer to practical antimatter applications. The future of antimatter research looks promising and full of potential. Government and private sector initiatives are driving forward the field of antimatter research. These initiatives are crucial for funding, technological development, and practical applications. Collaboration between these sectors accelerates progress and innovation. Governments around the world are investing heavily in antimatter research. National laboratories and research institutions receive significant funding to explore antimatter technology. This support is essential for large-scale experiments and infrastructure development. In the United States, NASA is exploring antimatter propulsion for deep space missions. Their initiatives aim to develop new propulsion systems that can drastically reduce travel time to distant planets. This research could revolutionize space exploration. The European Space Agency is also heavily involved. ESA funds various projects focused on antimatter containment and propulsion. These efforts are part of their broader goal to advance space technology and exploration. Private companies are entering the field with ambitious projects. Firms like SpaceX and Blue Origin are investing in advanced propulsion technologies, including antimatter. Their involvement brings additional resources and a drive for innovation. Collaborations between public and private sectors are becoming more common. Joint ventures leverage the strengths of both sectors, combining public funding with private ingenuity. These partnerships often result in faster development and deployment of new technologies. Startups specializing in antimatter technology are emerging. These companies focus on niche aspects such as efficient production or containment solutions. Their specialized expertise contributes to the overall advancement of the field. Government grants and contracts provide crucial support for these startups. Access to public funding allows small companies to undertake high-risk, high-reward projects. This funding is often a lifeline for groundbreaking research and development. International initiatives are also significant. Countries are forming alliances to share knowledge, resources, and technology. These global partnerships enhance collective capabilities and foster a collaborative environment. Regulatory bodies play an important role in overseeing these initiatives. Ensuring that research complies with safety and ethical standards is paramount. Regulations help prevent misuse and promote responsible development of antimatter technology. Educational initiatives funded by both sectors aim to build a skilled workforce. Universities and research institutions offer programs focused on antimatter science and engineering. These programs train the next generation of scientists and engineers. Public outreach is another focus of these initiatives. Educating the public about the potential benefits and risks of antimatter is important for gaining support. Outreach programs help demystify the science and build public trust. Incentives and awards are being established to encourage innovation. Government and private sector awards recognize significant advancements and breakthroughs. These incentives motivate researchers to push the boundaries of what is possible. Collaborative research centers are being established. These centers bring together experts from academia, industry, and government. They provide a hub for innovative research and development activities. The combined efforts of government and private sector initiatives are propelling antimatter research forward. By pooling resources and expertise, they are overcoming challenges and unlocking new possibilities. The future of antimatter technology looks increasingly promising, thanks to these collaborative efforts. Collaboration with space agencies is crucial for the advancement of antimatter research. These agencies bring extensive expertise and resources to the table. Joint efforts enable more ambitious projects and faster progress. NASA is a key player in antimatter research. They are exploring the use of antimatter propulsion for deep space missions. Collaboration with NASA provides access to cutting-edge technology and extensive research facilities. The European Space Agency, or ESA, is also deeply involved. ESA's projects on antimatter containment and propulsion are part of their broader space exploration goals. Partnering with ESA enhances the scope and impact of antimatter research. Russia's Roscosmos contributes significant experience in space technology. Their work in high-energy physics complements antimatter research efforts. Joint missions and projects with Roscosmos benefit from their extensive expertise. The Japan Aerospace Exploration Agency, JAXA, is another important collaborator. JAXA's innovative approaches to space exploration include research on antimatter. Their contributions help drive technological advancements in the field. China's CNSA is rapidly expanding its capabilities. Their investments in antimatter research are growing, making them a valuable partner. Collaboration with CNSA opens new opportunities for joint research and missions. These collaborations often involve sharing data and resources. This exchange accelerates research and development as agencies pool their findings and technology. Such cooperation is essential for tackling the complex challenges of antimatter research. Joint missions allow for practical testing of antimatter technology. By working together, space agencies can conduct more comprehensive experiments. These missions validate theoretical models and drive real-world applications. International partnerships also enhance funding opportunities. Collaborative projects can attract more substantial investment from multiple sources. This financial support is critical for large-scale research and development efforts. Standardizing protocols and safety measures is another benefit. Working together, agencies develop and adopt consistent standards. This ensures that antimatter research is conducted safely and ethically across the globe. Collaborations foster a sense of global scientific community. Researchers from different countries share their knowledge and expertise. This collective effort drives innovation and advances the field more rapidly. Educational exchanges are part of these collaborations. Scientists and engineers from different space agencies participate in joint training programs. This cross-training enhances skills and promotes a unified approach to antimatter research. Public engagement benefits from these partnerships. Collaborative projects often capture the public's imagination and interest. Increased awareness and support can drive further investment and progress. International competitions and challenges encourage innovation. Space agencies sponsor events that invite teams to solve complex problems related to antimatter. These competitions spur creativity and technological breakthroughs. The future of antimatter research is bright, thanks to these collaborations. By working together, space agencies can achieve more than they could alone. The shared goal of advancing space exploration unites these efforts, driving forward the potential of antimatter technology. Future research directions in antimatter technology are both exciting and challenging. Scientists are looking to increase the efficiency of antimatter production. Finding new methods to generate antimatter more cost-effectively is a top priority. Another key area is improving containment technology. Researchers are developing more stable and secure ways to store antimatter. This involves advancements in magnetic traps and cryogenic systems. The potential of antimatter propulsion continues to drive research. Future studies will focus on optimizing propulsion systems for longer missions. This includes enhancing thrust and fuel efficiency. Medical applications of antimatter are also a promising field. Research is ongoing into using antimatter for cancer treatment and imaging. These medical advancements could revolutionize healthcare. Understanding fundamental physics remains a core focus. Antimatter research helps us explore the basic laws of the universe. Future experiments aim to answer key questions about symmetry and the nature of matter. International collaborations will expand. Joint research projects between countries can pool resources and expertise. These partnerships are crucial for tackling the complex challenges of antimatter technology. Space exploration missions will incorporate more antimatter technology. Researchers are planning missions to test antimatter propulsion in space. These missions will provide valuable data and practical experience. Environmental impact studies are essential. Future research will evaluate the ecological effects of antimatter production and use. Sustainable practices will be developed to minimize any negative impacts. Advanced materials science will play a significant role. New materials that can withstand extreme conditions are being developed. These materials are crucial for building reliable containment and propulsion systems. Public and private sector partnerships will grow. Increased investment from private companies will drive innovation. These collaborations can accelerate the development of practical applications. Educational initiatives will continue to expand. Training programs for young scientists and engineers will focus on antimatter technology. This ensures a steady flow of talent into the field. Ethical considerations will guide future research. Ensuring that antimatter technology is used responsibly is paramount. Ethical guidelines and international agreements will be strengthened. Quantum computing could revolutionize antimatter research. Future studies will explore how quantum simulations can enhance our understanding. This technology promises to solve complex problems more efficiently. Robotic exploration will benefit from antimatter advances. Future missions will use antimatter-powered robots to explore distant worlds. These robots can travel farther and operate longer than current technology allows. The future of antimatter research is full of potential. Each new discovery and technological advancement brings us closer to unlocking the full capabilities of antimatter. The journey ahead is challenging, but the rewards promise to be transformative. A Mars mission with antimatter propulsion could revolutionize space travel. The significant reduction in travel time is one of the main advantages. Instead of months, the journey could take just weeks. Antimatter propulsion offers unparalleled efficiency. The energy density of antimatter is vastly higher than that of chemical fuels. This allows spacecraft to carry more payload while using less fuel. Increased payload capacity means more equipment, supplies, and scientific instruments can be transported. This enhances the mission's scientific return and the safety and comfort of the crew. A faster journey reduces the crew's exposure to space radiation. This is a critical factor in ensuring the health and safety of astronauts. Shorter trips also mean less psychological strain from prolonged isolation. The mission architecture would leverage antimatter's unique properties. A spacecraft designed for antimatter propulsion would include advanced containment systems. These systems ensure the safe storage and use of antimatter. The initial phase involves launching the spacecraft into Earth's orbit. From there, antimatter engines would ignite, propelling the craft toward Mars. This stage would demonstrate the viability of antimatter propulsion in deep space. Upon approaching Mars, the spacecraft would decelerate using antimatter thrusters. This controlled descent allows for precise landing, critical for mission success. Advanced landing systems would ensure a safe touchdown on the Martian surface. The mission would focus on extensive scientific exploration. Advanced instruments powered by antimatter energy could operate for extended periods. This enables detailed studies of Mars geology, climate, and potential for past life. Antimatter propulsion also supports return missions. The spacecraft can be designed for a round trip, bringing astronauts back to Earth. This ensures the mission's sustainability and opens the door for regular Mars expeditions. Long-term colonization plans benefit from antimatter technology. The ability to quickly and efficiently travel to Mars is a game changer. It supports the establishment of permanent human settlements. Collaborations with international space agencies will enhance the mission's success. Shared expertise and resources will be crucial for developing the necessary technology. Global cooperation ensures that the mission benefits all of humanity. Funding from both government and private sectors will be essential. The high costs associated with antimatter technology require substantial investment. However, the potential returns make it a worthwhile endeavor. The mission will also drive advancements in related technologies. Innovations in materials science, energy storage, and robotics will be critical. These advancements will have broader applications beyond space exploration. Public interest and support will be vital. A Mars mission with antimatter propulsion captures the imagination. Engaging the public through education and outreach ensures continued backing. This mission represents a monumental step forward in space exploration. The use of antimatter propulsion could transform our approach to reaching other planets. As we prepare for this journey, the possibilities seem boundless. Exploring the outer solar system presents incredible opportunities for discovery. Antimatter propulsion can drastically reduce travel times to these distant regions. This makes missions to the outer planets more feasible and ambitious. Jupiter and its moons are primary targets. With antimatter propulsion, we can reach Jupiter much faster than with traditional methods. This allows for extended missions to study its complex system of moons and massive storms. Saturn and its spectacular rings offer another fascinating destination. Faster travel times enable more detailed exploration of Saturn's unique features. Missions could focus on its rings, magnetic field, and diverse moon system. Titan, Saturn's largest moon, is of particular interest. Its thick atmosphere and liquid methane lakes make it a prime candidate for studying prebiotic chemistry. Antimatter-powered probes could spend more time investigating its surface and atmosphere. Beyond Saturn, Uranus and Neptune are often overlooked due to their distance. Antimatter propulsion can change this by making missions to these ice giants more practical. Detailed studies of their atmospheres, magnetic fields and moons would be possible. Kuiper Belt holds many secrets about the early solar system, home to dwarf planets like Pluto and Eris. This region is icy bodies. Antimatter propulsion could enable extensive exploration of this distant frontier. Further out lies the Oort cloud, a theoretical shell of icy objects surrounding the solar system. Reaching this area would provide insights into the solar system's boundary and the origins of comets. Antimatter technology could make such ambitious missions achievable. Long-duration missions benefit greatly from antimatter's efficiency. Probes can carry more scientific instruments and power them for extended periods. This ensures continuous data collection and high-resolution imaging. Advanced propulsion also allows for more flexible mission designs. Spacecraft can change trajectories and explore multiple targets in a single mission. This adaptability maximizes scientific returns. Collaborative missions with international space agencies will enhance our exploration efforts. Sharing knowledge and resources makes these complex missions more feasible. Global partnerships ensure that discoveries benefit all of humanity. The outer solar system is a frontier for astrobiology. Studying the moons of Jupiter and Saturn, like Europa and Enceladus, could reveal signs of life. Antimatter-powered missions can delve deeper into these intriguing environments. Investing in these missions drives technological innovation. The challenges of exploring the outer solar system push the boundaries of current technology. The advancements made will have broad applications beyond space exploration. Public engagement is crucial for supporting these missions. Highlighting the potential for groundbreaking discoveries can generate excitement and funding. Educational programs and media coverage will keep the public informed and involved. Exploring the outer solar system will expand our understanding of the universe. Each mission brings new data and insights that reshape our knowledge. The use of antimatter propulsion marks a new era in our quest to explore the cosmos. The future of space exploration is bright with antimatter technology. As we prepare to journey to the outer reaches of our solar system, the possibilities for discovery are endless. Together, we can unlock the mysteries of these distant worlds. Potential missions to exoplanets are becoming more feasible with advanced propulsion technologies. Antimatter propulsion could dramatically reduce travel times to these distant worlds. This opens up exciting possibilities for exploring planets outside our solar system. Identifying suitable exoplanet targets is the first step. Missions would likely focus on planets within the habitable zones of their stars. These regions offer the best chances of finding conditions suitable for life. The nearest exoplanet system, Alpha Centauri, is a prime candidate. With antimatter propulsion, a mission to Alpha Centauri could be completed within a human lifetime. This would be a monumental achievement in space exploration. Probes equipped with advanced sensors could study these exoplanets in detail. They could analyze atmospheric composition, surface conditions, and potential signs of life. This data would provide invaluable insights into the nature of other planetary systems. Interstellar communication is a key challenge for these missions. Developing reliable methods to send data back to Earth is crucial. Antimatter-powered spacecraft could carry advanced communication systems to overcome this hurdle. Collaborative efforts with international space agencies would be essential. Such ambitious missions require a global approach, pooling resources and expertise. Joint ventures can enhance the chances of mission success. Funding from both public and private sectors will be necessary. The high costs associated with interstellar travel demand substantial investment. However, the potential scientific returns justify these expenditures. The technology developed for exoplanet missions will have broader applications. Innovations in propulsion, materials science, and communications will benefit other fields. These advancements will drive progress in both space exploration and terrestrial technologies. Public engagement and support are vital. Highlighting the potential for discovering extraterrestrial life can capture the public's imagination. Educational programs and media campaigns can help maintain interest and funding. Ethical considerations must guide these missions. Ensuring that we do not contaminate other worlds is paramount. Strict planetary protection protocols will be necessary to preserve these environments. Robotic explorers will be the first to visit exoplanets. These robots can conduct detailed surveys and gather extensive data. Their findings will inform future missions and potentially pave the way for human exploration. Long-term planning is essential for these missions. The distances involved require careful consideration of mission duration and sustainability. Antimatter propulsion offers the best solution for managing these extended timelines. Scientific discoveries from exoplanet missions will have profound implications. They can expand our understanding of planetary formation, climate, and potential for life. Each mission brings us closer to answering fundamental questions about our place in the universe. Future generations will benefit from the knowledge gained. The exploration of exoplanets will inspire new scientific endeavors and technological innovations. It ensures that humanity continues to push the boundaries of what is possible. As we prepare for these incredible journeys, the excitement and potential are palpable. The exploration of exoplanets represents the next great leap in space exploration. With advanced propulsion and international collaboration, the stars are within our reach. Deep space probes are essential for exploring the far reaches of our solar system and beyond. Equipped with advanced technology, these probes can travel vast distances and send back valuable data. Antimatter propulsion could enhance their capabilities even further. One key advantage of antimatter-powered probes is their increased speed. They can reach distant destinations much faster than traditional probes. This allows for more timely data collection and analysis. Deep space probes can investigate a variety of targets, from the outer planets and their moons to distant asteroids and comets. These missions provide crucial insights. Each target offers unique opportunities for scientific discovery. The data collected by deep space probes helps us understand the fundamental processes of our solar system. Studying these distant objects reveals information about planetary formation and evolution. This knowledge is vital for piecing together the history of our cosmic neighborhood. Advanced sensors and instruments aboard these probes are essential. High-resolution cameras, spectrometers, and other tools enable detailed observations. These instruments can detect a wide range of phenomena, from surface features to atmospheric composition. Powering these instruments for long-duration missions is a significant challenge. Antimatter propulsion not only provides thrust, but can also generate energy for the probe systems. This dual functionality is a major advantage for deep space missions. Communication is another critical aspect. Deep space probes must transmit data back to Earth over vast distances. Reliable communication systems ensure that the valuable information they gather is received and analyzed. Autonomy is crucial for deep space probes. Given the communication delays, these probes must operate independently. Advanced AI and robotics enable them to conduct experiments and make decisions on their own. Durability and reliability are key factors in the design of deep space probes. They must withstand extreme conditions, from the cold of deep space to intense radiation. Robust engineering ensures that these probes can complete their missions successfully. International collaborations enhance the effectiveness of deep space probes. Sharing expertise and resources allows for more ambitious missions. Joint projects bring together the best minds and technologies from around the world. Funding from multiple sources is essential. Government space agencies, private companies, and international consortia all contribute. This collective investment supports the development and deployment of cutting-edge probes. Public interest in deep space missions is growing. These missions capture the imagination and inspire future generations of scientists. Public support helps secure the funding and political backing needed for these ambitious projects. The discoveries made by deep space probes have far-reaching implications. They expand our knowledge of the universe and our place within it. Each mission builds on the successes of the past and lays the groundwork for future exploration. Future probes will continue to push the boundaries of what is possible. As technology advances, these missions will become even more sophisticated. The next generation of deep space probes promises to unveil new mysteries and wonders. Deep space probes represent humanity's quest for knowledge and exploration. Their journeys to the farthest reaches of our solar system and beyond are a testament to our ingenuity and curiosity. With advanced propulsion and international collaboration, the future of deep space exploration is bright. Timeframes for mission feasibility are a critical aspect of planning. Determining how soon we can realistically achieve these advanced missions is essential. It involves assessing current technology, funding, and research progress. In the near term, we are looking at the next 10 to 20 years. During this period, advancements in antimatter production and containment are expected to mature. Initial missions may focus on testing these technologies in space. For missions to Mars using antimatter propulsion, feasibility could be within 20 to 30 years. This time frame allows for the development and testing of propulsion systems. It also includes planning and building the necessary infrastructure. Exploring the outer solar system with antimatter-powered probes might be feasible within 30 to 40 years. This period accounts for developing reliable long-duration mission technologies. It also includes international collaboration and securing funding. Interstellar missions to nearby star systems are a longer-term goal. Feasibility for such missions could be within 50 to 100 years. Significant advancements in propulsion, energy storage, and autonomous systems are required. Continuous research and development are crucial to meet these timeframes. Government and private sector investment must be sustained. Long-term commitment ensures that technologies remain on track. Incremental testing and missions will pave the way. Each successful mission builds confidence and refines the technology. This step-by-step approach is essential for managing risks and ensuring mission success. Collaboration with international space agencies will accelerate progress. Sharing knowledge and resources can reduce costs and development time. Joint missions and projects benefit from a diverse pool of expertise. Public support and interest are vital for maintaining momentum. Engaging the public through education and outreach can help secure ongoing funding. Public enthusiasm drives political and financial backing. Ethical and regulatory frameworks need to be developed concurrently. Ensuring that missions adhere to ethical standards is crucial. Regulations must evolve to address new technologies and potential risks. Robust testing and validation processes are necessary. Extensive ground-based and near-Earth tests will precede deep space missions. These tests help identify and mitigate potential issues. Educational initiatives will prepare the next generation of scientists and engineers. Investing in education ensures a skilled workforce ready to tackle future challenges. This long-term investment is critical for sustained progress. As technology advances, timelines may be adjusted. New discoveries and breakthroughs can accelerate mission feasibility. Staying adaptable and responsive to changes is essential. Milestones and checkpoints will guide the progress of these missions. Setting clear goals and tracking achievements helps maintain focus. Regular assessments ensure that missions remain on schedule. Ultimately, the timeframes for mission feasibility reflect our dedication to exploration. They embody the collective effort of the global scientific community. With determination and collaboration, we can achieve these ambitious goals. Depictions of antimatter in science fiction have fascinated audiences for decades. These stories often explore the immense potential and dangers of antimatter. They provide a glimpse into how this technology might shape our future. One of the most famous examples is in Star Trek. The starships in this universe use matter-antimatter reactors for propulsion. This depiction has influenced public perception of antimatter's potential. In Dan Brown's novel Angels and Demons, antimatter is portrayed as a powerful and dangerous substance. The plot revolves around a stolen canister of antimatter that could cause a massive explosion. This story highlights the potential risks associated with antimatter. Isaac Asimov's works also explore antimatter. In his Foundation series, antimatter is used as a highly efficient energy source. Asimov's vision showcases the benefits of harnessing antimatter for advanced technologies. The video game series Mass Effect features antimatter as a key component of its starship engines. This depiction emphasizes antimatter's role in enabling faster-than-light travel. It reflects the scientific aspirations for antimatter propulsion. Arthur C. Clarke's novel, 3001. The Final Odyssey presents antimatter as a solution for interstellar travel. The use of antimatter engines allows humanity to explore distant stars. Clarke's work underscores the transformative potential of antimatter. In the television show Stargate SG-1, antimatter is used in advanced alien technologies. These technologies demonstrate the power and efficiency of antimatter-based systems. The show explores both the benefits and dangers of such technology. Antimatter is also featured in the novel Ringworld by Larry Niven. The characters use antimatter as a weapon, highlighting its destructive potential. This portrayal addresses the ethical concerns surrounding antimatter's use. The movie Sunshine depicts a mission to reignite the sun using an antimatter bomb. This extreme scenario showcases antimatter's vast energy potential. It also raises questions about the ethical implications of using such powerful technology. In the anime series Cowboy Bebop, antimatter drives are used for space travel. The series presents antimatter as a commonplace technology in the future. This depiction normalizes the use of antimatter in everyday life. The novel Revelation Space by Alistair Reynolds explores antimatter as a weapon and energy source. The story delves into the complexities and dangers of antimatter technology. It reflects the dual-use nature of antimatter in both civilian and military contexts. In James Rollin's novel Black Order, antimatter is part of a secret Nazi experiment. The story intertwines historical fiction with advanced science. This narrative highlights the speculative and sometimes controversial nature of antimatter research. Science fiction often exaggerates the capabilities of antimatter. These stories stretch the current scientific understanding to explore what-if scenarios. They serve to inspire and caution readers about future possibilities. The consistent theme in these depictions is antimatter's immense power. Whether as a propulsion system, energy source, or weapon, antimatter is shown as transformative. Science fiction uses antimatter to explore both utopian and dystopian futures. These stories also influence public interest in antimatter research. They spark curiosity and drive discussions about the potential and risks of this technology. Science fiction thus plays a role in shaping the future of antimatter exploration. Public understanding and misconceptions about antimatter are widespread. Many people first encounter the concept of antimatter through science fiction. This often leads to both fascination and misunderstanding. One common misconception is that antimatter is purely fictional. In reality, antimatter is a well-established scientific concept. It has been experimentally produced and studied for decades. Another misconception is that antimatter is universally destructive. While antimatter can release tremendous energy when it meets matter, it can also be harnessed for beneficial purposes. Its potential applications in energy and propulsion are promising. Many people believe that antimatter is abundant and easily accessible. In fact, antimatter is extremely rare and difficult to produce. Current production methods are highly inefficient and costly. There is also confusion about the safety of antimatter. While it must be handled with extreme care, advances in containment technology are making its storage increasingly safe. Properly managed, antimatter can be a viable energy source. Public understanding is often influenced by sensationalized media. Dramatic portrayals of antimatter in movies and books can distort its scientific realities. Educational efforts are needed to provide accurate information. Some people think antimatter could solve all our energy problems overnight. While it has immense potential, significant technical challenges remain. Research and development are crucial before it can be widely used. There is a misconception that antimatter research is universally supported. In reality, funding and political support can be inconsistent. Advocating for sustained investment is important for progress. Many are unaware of the current practical applications of antimatter. For example, positron emission tomography, PET, scans in medical imaging use antimatter. This demonstrates its potential beyond theoretical scenarios. The complexity of antimatter physics can be a barrier to public understanding. Simplifying concepts without oversimplifying the science is a challenge for educators. Effective communication is key to bridging this gap. Some believe that antimatter weapons are already a significant threat. While the potential for weaponization exists, current capabilities are far from this reality. Ongoing ethical discussions aim to prevent such developments. Public engagement initiatives are vital for improving understanding. Science museums, documentaries, and outreach programs play a crucial role. They make the science accessible and relatable to a broader audience. Educational institutions have a responsibility to address misconceptions. Including antimatter in curricula can foster a more informed public. Early education in these concepts can inspire future generations of scientists. Social media can both help and hinder public understanding. It spreads information quickly, but can also propagate myths. Encouraging critical thinking and scientific literacy is essential. Accurate public understanding of antimatter is important for its future development. Misconceptions can lead to fear or unrealistic expectations. Clear, factual communication helps build informed support for ongoing research and applications. Educational outreach programs are crucial for increasing public understanding of antimatter. These programs aim to demystify the science and make it accessible to everyone. They play a vital role in inspiring the next generation of scientists. Museums and science centers often feature interactive exhibits on antimatter. These exhibits allow visitors to explore antimatter concepts hands-on. Engaging displays and demonstrations help to simplify complex ideas. Documentaries and television programs about antimatter reach a wide audience. They can explain the science behind antimatter in an entertaining and informative way. High-quality visual effects and expert interviews make the subject more relatable. Public lectures and seminars offer another way to engage with the community. Scientists and researchers can share their work and answer questions. These events foster direct interaction and deeper understanding. School programs and workshops bring antimatter education to students. Tailored lessons and activities can make learning about antimatter fun and engaging. Early exposure to these topics can spark a lifelong interest in science. Online platforms and social media are powerful tools for educational outreach. Short videos, articles, and interactive content can reach a global audience. They provide accessible and flexible ways to learn about antimatter. Partnerships with educational institutions enhance the reach of outreach programs. Universities and colleges can collaborate on public events and resources. These partnerships strengthen the connection between research and education. Interactive simulations and virtual reality experiences offer immersive learning opportunities. These technologies allow users to explore antimatter concepts in a hands-on way. They make abstract ideas more concrete and understandable. Citizen science projects involve the public in real research. Participants can contribute to antimatter studies and data collection. This active involvement makes the science more tangible and personal. Publications and books aimed at general audiences can also be effective. Well-written and engaging text can explain antimatter in an accessible way. They provide in-depth information for those who want to learn more. Science festivals and fairs provide a fun and interactive environment for learning. They bring together a wide range of scientific topics, including antimatter. These events encourage curiosity and exploration. Teacher training programs ensure that educators have the resources they need. Providing teachers with up-to-date information and tools enhances classroom learning. It equips them to inspire their students with the wonders of antimatter. Collaboration with media outlets can amplify the reach of educational content. News articles, TV segments, and radio programs can highlight important developments. They keep the public informed about the latest research and discoveries. Competitions and challenges can motivate students and the public to engage with antimatter science. Contests for designing experiments or solving problems related to antimatter stimulate creativity. They encourage a deeper understanding through active participation. Effective educational outreach creates a well-informed public that supports scientific research. By making antimatter science accessible and engaging, these programs help ensure that the next generation is ready to take on the challenges and opportunities of the future. Media influence on public opinion is significant, especially regarding scientific topics like antimatter. News outlets, movies, and TV shows shape how people perceive antimatter technology. Accurate and balanced reporting is crucial for fostering informed opinions. Movies and TV shows often dramatize antimatter for entertainment. While this captures interest, it can also lead to misconceptions. Fictional portrayals sometimes exaggerate the dangers or simplify the science. News media play a key role in educating the public. Quality journalism can explain complex scientific concepts in an understandable way. However, sensational headlines can distort the reality of antimatter research. Documentaries offer a more in-depth look at antimatter science. They can provide detailed explanations and showcase real-world applications. Well-produced documentaries help demystify antimatter for a broad audience. Social media platforms amplify the reach of information. Scientists and educators use these platforms to share insights and updates. However, misinformation can spread quickly, complicating public understanding. Educational YouTube channels are particularly effective. They combine visual aids with clear explanations to make antimatter accessible. These channels reach diverse audiences, from students to lifelong learners. Print media, including magazines and newspapers, also influence public opinion. Articles written by knowledgeable science writers can clarify antimatter's potential and challenges. Consistent coverage keeps the topic in public discourse. Radio and podcasts provide another avenue for spreading information. Interviews with experts allow for nuanced discussions. Listeners gain a deeper understanding through extended conversations. Public figures and influencers can sway opinions significantly. When they speak accurately about antimatter, they help educate their followers. Misinformation from these figures, however, can have widespread negative effects. Interactive media, such as apps and online games, engage younger audiences. They introduce scientific concepts in a fun and engaging way. These tools can spark interest and curiosity about antimatter. Collaborations between media producers and scientists improve content accuracy. Consulting with experts ensures that media representations are factual. This collaboration enhances the credibility of the information presented. Public trust in media sources affects the reception of information. Trusted sources are more likely to be believed and shared. Building and maintaining this trust is essential for effective communication. Media coverage often peaks around significant scientific breakthroughs. Highlighting these moments can inspire public interest and support for research. Continuous coverage maintains awareness and engagement. Educational campaigns can counteract misinformation. Clear, accurate information distributed through various media channels helps correct false narratives. These campaigns play a critical role in public education. Overall, the media's influence on public opinion is powerful. Accurate, engaging, and well-researched content can enhance understanding and appreciation of antimatter. Responsible media practices ensure that the public remains well-informed and supportive of scientific advancements. The role of social media and online platforms in shaping public understanding of antimatter is significant. These platforms provide a space for scientists to share their research and engage with the public. They offer immediate access to information and foster interactive learning. Scientists and educators use social media to disseminate accurate information about antimatter. Platforms like Twitter and Instagram allow them to reach a broad audience quickly. Engaging posts and threads can spark curiosity and encourage further exploration. Online platforms like YouTube host educational videos that explain antimatter concepts. Channels dedicated to science communication break down complex topics into digestible content. Visual aids and animations enhance comprehension. Discussion forums such as Reddit provide spaces for in-depth conversations. Subreddits focused on science and technology enable users to ask questions and share knowledge. These discussions can clarify misconceptions and provide diverse perspectives. Blogs and personal websites allow scientists to write detailed articles about their work. These platforms give researchers the freedom to explain their findings in their own words, They can also share updates and insights from their ongoing projects. Interactive content, like quizzes and simulations, can engage users in learning about antimatter. Websites and apps offer tools that make learning about antimatter fun and interactive. This hands-on approach helps solidify understanding. Social media campaigns can raise awareness about antimatter research. Hashtags and challenges can create viral moments that draw attention to scientific topics. These campaigns leverage the network effect to spread information widely. Online platforms enable live streaming of lectures and events. Scientists can host webinars and Q&A sessions to discuss antimatter with the public. Real-time interaction makes these sessions dynamic and engaging. Podcasts provide another medium for deep dives into antimatter topics. Science-focused podcasts often feature experts discussing their work in detail. These conversations offer listeners a more nuanced understanding. Crowdfunding platforms can support antimatter research projects. Researchers can raise funds from the public to finance their experiments. This democratizes funding and involves the community in scientific endeavors. Social media influencers and popular science communicators play a key role. When they share accurate information about antimatter, they reach a wide audience. Their endorsements can build interest and credibility. Misinformation is a significant challenge on social media. False claims and sensational stories about antimatter can spread quickly. Fact-checking and promoting reliable sources are essential to combat this issue. Online platforms also enable collaboration among scientists. They can share data, publish findings, and discuss theories in virtual spaces. This fosters a global scientific community working together on antimatter research. Educational institutions use social media to promote their programs and discoveries. Universities and research centers share news and achievements with a broader audience. This transparency builds trust and showcases the importance of their work. Overall, social media and online platforms are powerful tools for science communication. They can enhance public understanding and support for antimatter research. Responsible use of these platforms ensures accurate information reaches the public. A cost-benefit analysis of antimatter propulsion is essential to understand its feasibility. The high costs associated with antimatter production are a major factor. Currently, producing even small amounts of antimatter is extremely expensive. Developing antimatter propulsion systems also requires significant investment. This includes research and development, manufacturing, and testing. The initial costs are high, but the potential benefits may justify these expenditures. One of the main benefits is the potential for drastically reduced travel times. Antimatter propulsion could cut travel time to Mars from months to weeks. This efficiency can significantly lower mission costs over time. Another benefit is the increased payload capacity. Antimatter's high energy density means less fuel is needed. This allows for more scientific instruments and supplies to be carried on missions. Antimatter propulsion could enable missions to the outer solar system and beyond. The ability to reach distant destinations faster opens up new possibilities for exploration. This can lead to groundbreaking scientific discoveries. The potential for interstellar travel is another major benefit. Antimatter propulsion could make it possible to reach nearby star systems within a human lifetime. This would be a monumental achievement in space exploration. There are also environmental considerations. Antimatter propulsion, if developed responsibly, could reduce the need for chemical propellants. This can decrease the environmental impact of space missions. However, safety concerns must be addressed. The containment and handling of antimatter require advanced technology and strict protocols. Ensuring the safety of missions and personnel is a significant challenge. Public perception and support play a role in the cost-benefit analysis. Positive public opinion can drive funding and investment. Transparent communication about the benefits and risks is crucial. International collaboration can help spread the costs and share the benefits. Joint efforts with other space agencies can reduce individual financial burdens. This collective approach enhances the feasibility of antimatter propulsion. Technological advancements can lower costs over time. As research progresses, more efficient production and containment methods may be developed. Continuous innovation is key to making antimatter propulsion viable. Economic benefits extend beyond space exploration. Advances in antimatter technology can lead to new industries and job creation. The spin-off technologies can have wide-ranging applications. The long-term benefits of antimatter propulsion could outweigh the initial costs. The potential for rapid space travel and expanded exploration is transformative. Careful planning and investment can help realize these benefits. Balancing the costs and benefits requires strategic decision-making. Policymakers must consider both the immediate expenses and the long-term gains. A well-structured approach ensures sustainable development of antimatter propulsion. Ultimately, the cost-benefit analysis highlights the immense potential of antimatter propulsion. While challenges exist, the transformative benefits for space exploration and beyond are compelling. Continued research and international cooperation will be crucial in advancing this promising technology. Funding and investment opportunities for antimatter research are crucial for its advancement. Both public and private sectors play significant roles in providing financial support. Government grants and private investments are essential to drive innovation. National space agencies are key sources of funding. Organizations like NASA, ESA, and Roscosmos allocate budgets specifically for advanced propulsion research. These funds support both fundamental research and applied technology development. Private companies are increasingly interested in antimatter technology. Tech giants and aerospace firms see the potential for transformative advancements. Their investments bring additional resources and expertise to the field. Venture capital is another avenue for funding. Startups working on antimatter applications can attract venture capitalists looking for high-risk, high-reward opportunities. This funding helps bring innovative ideas to market. Public-private partnerships offer substantial benefits. Collaborative projects can leverage government funding and private sector efficiency. These partnerships enhance the scope and impact of research initiatives. Crowdfunding platforms can also support antimatter research. Scientists and researchers can reach out to the public for financial backing. This approach democratizes funding and raises public awareness. International collaborations increase funding opportunities. Joint projects between countries can pool resources and share costs. These collaborations facilitate larger and more ambitious research programs. Philanthropic foundations are another source of funding. Organizations dedicated to scientific advancement often provide grants for cutting-edge research. Their support is crucial for high-risk exploratory projects. Academic institutions play a vital role in securing funding. Universities often receive grants for research and development. Collaboration with industry partners can further enhance these opportunities. Competitions and challenges can drive innovation. Offering prizes for specific advancements in antimatter technology motivates researchers. These competitions attract diverse talent and fresh ideas. Long-term funding commitments are essential. Sustained investment over multiple years ensures continuous progress. It allows researchers to undertake comprehensive studies and develop practical applications. Tax incentives can encourage private investment. Governments can offer tax breaks to companies investing in antimatter research. These incentives make high-risk investments more attractive. Transparency in funding allocation is important. Clear communication about how funds are used builds trust with investors. It ensures that resources are effectively utilized for maximum impact. Educational grants support the development of future scientists. Scholarships and fellowships in antimatter research attract young talent. Investing in education ensures a steady pipeline of skilled researchers. Finally, a diversified funding strategy is key to success. Combining resources from various sectors mitigates financial risk. It provides a stable foundation for the ambitious pursuit of antimatter technology. The impact of antimatter technology on the space industry could be revolutionary. Antimatter propulsion offers unprecedented speed and efficiency for space travel. This advancement can significantly reduce mission durations and expand exploration horizons. Spacecraft equipped with antimatter engines could reach distant planets in a fraction of the current time. This would make manned missions to Mars and beyond more feasible. The reduced travel time would also decrease the risks and costs associated with long-duration missions. Satellite deployment could become more efficient and cost-effective. Antimatter propulsion systems could launch heavier payloads with greater precision. This enhances the capabilities of communication, weather, and navigation satellites. The space tourism industry stands to benefit immensely. Faster travel times make it possible to offer more ambitious space tourism packages. Tourists could experience trips to the Moon or Mars, opening new revenue streams. Asteroid mining could become a viable industry. Antimatter propulsion allows for quicker and more frequent missions to asteroid belts. Extracting valuable minerals from asteroids could revolutionize the global resource market. Space station logistics would improve with the advent of antimatter technology. Resupplying stations like the ISS would be faster and more reliable. This supports long-term habitation and scientific research in orbit. Deep space exploration missions would see a significant boost. Probes powered by antimatter could explore the outer planets and beyond with unprecedented efficiency. This expands our scientific understanding of the solar system and the universe. Antimatter technology could lead to new space infrastructure developments. Advanced propulsion systems enable the construction of larger and more complex space habitats. These structures could support scientific, commercial, and even residential activities in space. The defense sector might also see advancements. Antimatter propulsion offers strategic advantages for national security missions. Rapid deployment and maneuverability in space are crucial for future defense capabilities. Collaboration between space agencies and private companies will be essential. Joint ventures can leverage antimatter technology to achieve shared goals. This fosters innovation and accelerates the development of new applications. Regulatory frameworks will need to evolve. The introduction of antimatter technology requires updated space laws and safety regulations. Ensuring safe and ethical use of antimatter is paramount. Investment in research and development will surge. Companies and governments will increase funding to capitalize on antimatter's potential. This financial support drives further innovation and commercialization. Public interest in space exploration will grow. The possibilities offered by antimatter technology capture the imagination. Increased public support can lead to greater funding and political backing. Education and workforce development will need to keep pace. Preparing a skilled workforce to handle advanced antimatter systems is crucial. Training programs and academic curricula must adapt to these new technological demands. Ultimately, the integration of antimatter technology will transform the space industry. From faster travel and enhanced exploration to new commercial opportunities, the potential impacts are vast. The future of space exploration and industry is set to enter an exciting new era. Potential markets for antimatter extend far beyond space exploration. The medical industry could see revolutionary changes with the use of antimatter. Positron emission tomography, or PET scans, already use antimatter for detailed imaging. Antimatter could be harnessed for cancer treatment. Antimatter beams might target and destroy cancer cells with unprecedented precision. This could lead to more effective and less invasive treatments. Energy production is another significant market. Antimatter's energy density far exceeds that of conventional fuels. Developing antimatter reactors could revolutionize how we generate and store energy. In the transportation sector, antimatter propulsion could redefine air and space travel. Faster, more efficient travel would benefit commercial airlines and private spaceflight companies. This technology promises to drastically reduce travel times. The defense industry is also a potential market. Antimatter weapons, while controversial, could be developed for strategic purposes. Additionally, antimatter propulsion could enhance military spacecraft capabilities. Scientific research would greatly benefit from antimatter. High-energy physics experiments often rely on antimatter particles. Increased availability of antimatter could accelerate discoveries in fundamental physics. The mining industry could exploit antimatter for resource extraction. Antimatter-powered equipment could operate more efficiently in extreme environments. This is particularly relevant for asteroid mining and deep-sea exploration. Telecommunications might also see advancements. Antimatter could power next-generation satellites and communication devices. This would improve global connectivity and data transmission speeds. Consumer electronics could experience a revolution. Antimatter batteries would offer significantly longer life and higher performance. This would impact everything from smartphones to electric vehicles. Healthcare logistics could benefit from antimatter technology. Faster transportation of medical supplies and organs would save lives. Antimatter-powered drones and aircraft could revolutionize medical logistics. The construction industry might use antimatter in advanced building techniques. Antimatter's energy could power new types of machinery. This would enable more efficient construction processes. Environmental technology is another promising market. Antimatter could be used in clean energy solutions. This includes powering devices that remove pollutants from the air and water. Educational institutions could use antimatter for advanced research and training. Universities and research centers would benefit from the availability of antimatter. This supports the development of new technologies and scientific advancements. The entertainment industry could also see novel applications. Theme parks and virtual reality experiences might use antimatter-powered technology. This would create more immersive and thrilling attractions. Overall, the potential markets for antimatter are vast and varied. From healthcare and energy to defense and consumer electronics, antimatter holds the promise of groundbreaking advancements. The challenge lies in developing the technology to harness its full potential. Long-term economic benefits of antimatter technology could be transformative. As production and containment methods improve, costs will decrease. This makes antimatter applications more accessible and widespread. Space exploration costs could significantly drop. Antimatter propulsion reduces fuel requirements and travel time. This efficiency translates to lower mission expenses and higher return on investment. Economic growth could be stimulated by new industries. Antimatter technology will likely create jobs in research, engineering, and manufacturing. These new sectors will contribute to economic diversification. The energy sector could undergo a revolution. Antimatter reactors promise clean and almost limitless energy. This could reduce dependence on fossil fuels and decrease energy costs globally. Healthcare advancements will lead to economic savings. More effective treatments and diagnostics mean reduced healthcare costs. This increases productivity and improves quality of life. Transportation industries will benefit from faster, more efficient travel. Reduced travel times enhance business operations and logistics. This has a positive ripple effect on global trade and commerce. The defense sector will see economic advantages. Enhanced capabilities from antimatter propulsion and weapons increase national security. This can deter conflicts and protect economic interests. Scientific research will drive technological innovation. Antimatter's role in high-energy physics can lead to breakthroughs in other fields. These discoveries often have commercial applications, further boosting the economy. Resource extraction becomes more efficient with antimatter technology. This is particularly relevant for rare and valuable materials. Enhanced mining techniques can increase supply and lower costs. Telecommunications advancements will spur economic growth. Faster and more reliable communication infrastructure supports global business. Improved connectivity drives innovation and economic activity. Consumer electronics will benefit from longer-lasting batteries. This reduces the frequency of replacements and lowers electronic waste. Consumers save money, and manufacturers can offer more competitive products. Educational institutions will see long-term benefits. Access to antimatter technology enhances research capabilities. This attracts talent and investment, driving educational and economic growth. Environmental technologies will mitigate the impacts of climate change. Antimatter-powered clean energy solutions can reduce carbon footprints. Sustainable practices support long-term economic stability. The entertainment industry will generate new revenue streams. Antimatter technology will create novel and exciting experiences. This attracts tourism and consumer spending. Overall, the integration of antimatter technology will drive long-term economic growth. The initial investment in research and development will yield substantial returns. As these technologies mature, the global economy will reap significant benefits. In this video, we explored the groundbreaking potential of antimatter technology and its revolutionary impact on space travel. We began by discussing how antimatter is produced, using advanced particle accelerators and sophisticated containment systems. Understanding these foundational aspects is crucial as we move toward practical applications. We then delved into the incredible energy yield from antimatter-matter collisions. This immense energy potential is what makes antimatter so promising for space propulsion, offering the possibility of drastically reduced travel times. We examined the basics of antimatter propulsion, including direct annihilation propulsion and antimatter-catalyzed nuclear pulse propulsion. The discussion continued with an exploration of beam-core antimatter rockets and their theoretical efficiency and speed. These advanced propulsion methods could enable unprecedented travel speeds, making interstellar missions feasible within human lifetimes. We also touched on the current state of antimatter production and the challenges of scaling up for practical use. Safety concerns, particularly radiation shielding, were highlighted as critical considerations for future antimatter applications. The cost of production remains a significant barrier, but the long-term benefits and potential markets for antimatter technology offer compelling reasons to pursue this research. We explored potential applications beyond space travel, including energy production, medical advancements, and industrial uses. Collaborations with leading research institutions and international space agencies are vital for overcoming these challenges. Recent breakthroughs in antimatter research demonstrate the progress being made, and government and private sector initiatives are driving further advancements. Educational outreach programs and media influence play a crucial role in shaping public understanding and support for antimatter research. Social media and online platforms are powerful tools for engaging with the public and disseminating accurate information. A cost-benefit analysis of antimatter propulsion highlighted the significant potential benefits, despite the high initial costs. Funding and investment opportunities from various sources are essential for sustaining research and development. The impact on the space industry could be transformative, with faster travel, increased payload capacity, and new commercial opportunities. Potential markets for antimatter extend beyond space exploration, including energy, healthcare, and transportation. Long-term economic benefits could be substantial, driving innovation, job creation, and sustainable growth. As we conclude, it's clear that antimatter technology holds immense promise for the future. The journey to harness its full potential is challenging, but rewarding. If you enjoyed this video, please like and subscribe to our channel for more insightful content. Don't forget to check out the rest of our videos, where we explore other fascinating topics in science and technology. Your support helps us continue to bring you high-quality educational content. Thank you for watching, and we look forward to exploring the universe together with you.